Mr. Rosatos, are you back?
I am. Hear me? Can you hear me, Mr. Hearing Officer?
Yes,
Okay, yes, I'm here.
All right. The commission ready to proceed?
Yes, we are.
All right. And Madam Court Reporter, are we back on the record?
Yes, sir, we're on the record.
All right. And Ms. Apodaca, I saw you hit the record button, so I'll just remind Dr. Davidson you're still under oath and turn it back over to Mr. Waymeyer.
Thank you. Coming back to qualifications and some of the data relied on here, have you had experience with residual oil zone development before this engagement?
Not directly, no.
So as we talk about the work of Mr. Meltzer and Bob Trenholm, this would be your first residual oil zone project, correct?
As they define it, yes, but we deal with the residual oil all the time in what I do. And so it wouldn't be the first time I've dealt with doing evaluation through an interval that has residual oil. It'd be the first time that I've done it in terms of an ROZ as defined by Trentham is a EOR project.
Now, in terms of, I want to talk about some of the work done. Jonathan Martell actually did a great deal of the work here for you, didn't he?
He did the actual push the buttons to run the model.
Did he not also build the databases and build the computer models?
Well, we build the models together jointly. We write the code. He's responsible for populating the databases and getting the data ready for input and output.
And so Mr. Martell did all of that work, yes?
It's Markel, by the way.
K with a K?
Markel.
Okay. And we haven't seen any witness statements in this case from Mr. Markel, have we?
You have not.
Now, coming back to the facies and visiting about how important the rock facies are. And I want to kind of frame some of this oil in place. If, for purposes of your oil in place, if there was less, based on your modeling, if there was less than 20% residual, strike that. If there was less than 20% oil saturation, you with me so far?
Mm-hmm.
You can tell the commissioners that your model credits zero oil towards the oil in place volumes, isn't that right?
In the summations that are generated to, I'll put it this way, in the intervals that exceed 20% oil saturation, all oil is counted. In intervals that are 20% or less than 20% oil saturation, we don't count them because one, there's two reasons for it. One, after 40 years.
And Dr. Davidson, this was a yes or no question. If in your model, in terms of telling these commissioners about opinions as to oil in place, if it is below, under your modeling, 20% oil saturation, zero of those volumes are credited, isn't that
Zero of
true?
those feet are credited.
Likewise, as we talk about permeability, if, based on your modeling, a interval has less than 1 millidarcy of permeability, your model credits zero oil for any oil in place that would be in an environment at, according to you, less than 1 millidarcy. Isn't that correct?
That's not correct.
Explain that.
Okay, our cutoff is 1/10 of a millidarcy. And when that's our cutoff, and we don't actually use the permeability calculate that, we use a 7% porosity cutoff, which came from a permeability porosity cutoff with the available core data using 1/10 of a millidarcy as a cutoff permeability. So the permeability cutoff is actually 0.1 millidarcy. And then for the assumption of, is there a vertical barrier or not, we take the vertical to horizontal permeability that came out of Seminole San Andres, and then use that to generate flags that indicate the existence of potential barriers. But those barriers aren't used in our modeling for oil in place. Those were flags to demonstrate the location of potential barriers at the request of, because I was asked to identify potential barriers as a part of my evaluation. But as far as the cutoffs, as far as in oil in place, those were not used.
Additionally, just big picture so that we don't lose the forest. Did you use 7% effective porosity or 7% total porosity?
As it came out of the model, it would have been effective.
And so if there was oil in intervals that you assessed at being less than 7% effective porosity, there's also zero oil credited in your oil in place volumes at those intervals. Isn't that right?
That's correct.
With respect to data here, you also have had zero oil samples out of the EMSU. Isn't that correct?
Oil samples out of the USU. I don't hold an oil sample from the SU. No, I don't have one in my office.
You also have performed no oil miscibility studies within the EMSU, and you haven't seen any either, have you?
As a part of my job. It wasn't part of what I was hired to do.
With respect to EOR and CO2 injection, that's going to lower the porosities and the permeabilities that otherwise that otherwise might be perceived as cutoffs in a conventional primary recovery. Isn't that right?
I don't agree with that.
Let's get into, we've talked about some of the geology and that you're not a geologist. I want to go to one of the slides that you used earlier. So there was a lot of would you agree that there was a lot of geology discussed in your opening remarks with Mr. Rankin?
I discussed depositional environments.
That's really more of a geology thing, isn't it?
It's part of petrophysics. Big part of petrophysics.
I want to ask in terms of the karsting that you described, can you describe to the commissioners, how does karsting occur?
There's a lot of different ways that it can occur. Shallow, the theory is that you have meteoric waters, which would be fresh waters, penetrating exposed carbonate surfaces and creating dissolution and where the water penetrates, and that could create karst. The way it was described by Dr. Lindsay was it created kind of sinkholes that ultimately filled in with other materials. That would be what I would call top-down karsting. We see that sort of thing routinely in San Andres. Another type of karsting occurs due to the movement of acidic waters through the rock where you get dissolution precipitation reactions and where the rock is dissolved, generally moves through the higher permeable fluids, move through the higher permeable rock, and you start generating pathways, dissolution pathways between the vugs, and then ultimately the vugs get connected and enlarged, and then when they become large enough, you can get something called a collapse breccia, where the rock actually collapses in on itself, and that's a different type of karsting.
All of that is happening at the surface level in shallow water environments, isn't it?
I don't really agree that the massive karsting that comes from the model that Bob Lindsay put together with the counterflow of H2S in meteoric waters, I'm not sure that, I don't think that's a surface phenomenon, no.
In terms of evaporation and evaporative cycles, this isn't happening to get this evaporation, that has to happen at the surface.
Well, evaporation doesn't have anything to do with the karsting. The evaporation, it has to do with the development of the evaporite layers.
I want to go because I think we can short circuit a lot of this. At slide 16, in response to Mr. Rankin's questions, you shared with the commissioners your opinion that the San Andres was a high energy environment. Is that right?
The upper San Andres is in a high energy environment. So above what I'd call the high gamma ray marker, it was a higher energy environment. And then below the gamma ray marker, I'm moving more towards the outer ramp environment where sea level changes can dramatically change the characteristics of the rock over short distances.
Okay. In your earlier testimony, you described all the way through the San Andres that it is a high energy environment. Are you changing that testimony now?
I didn't, no, that's not why I testified at all. I said the Grayburg San Andres interval above that marker is generally a high energy environment. Below that marker where the gamma ray baseline shifts, I'm moving to a high frequency environment where I'm seeing very rapid sea level shifts where the rock quality is changing from good to medium with these evaporite boundaries on it. And then as I move deeper in the San Andres, I'm moving more and more into a deeper water, lower energy environment.
You describe anhydrites throughout the lower San Andres, yes?
We see evidence of them. Now, they're not all layered in. They're not all bedded anhydrites.
Anhydrites are going to be formed at the surface, aren't they?
That's correct.
And you heard Dr. Lindsay's testimony that this was not a deep water environment here at the EMSU for the San Andres. Do you remember that testimony?
I don't know that he said for the San Andres, because I don't think he looked at any San Andres cores here. He said that there were no bedded anhydrites in the Grayburg or in the upper San Andres in the cores that he reviewed. He said there was only anhydrite cements.
My question was, you do not recall Dr. Lindsay testifying that the San Andres at this particular EMSU location would have been a shallow water environment, not a deep water environment?
Well, if he said it, I don't agree with it.
And with respect to the qualifications as a geologist, you would have to tell the commissioners that Dr. Lindsay is far more qualified than you as a geologist. Isn't that right?
I don't know that he was describing the San Andres underneath the high gamma ray marker. There tends to be a tendency to define the San Andres as what has been seen in the core and ignore that it could be different deeper in the section.
Would you want core to be able to say it is different?
I can see that it's different from the gamma ray response.
Well, let's talk about the gamma ray response. Now, the gamma ray there would be, according to you, measuring uranium, correct?
That's correct.
How do you know, since you don't have spectral gamma, that it is not measuring potassium or thorium?
Because everywhere I've looked at spectral gamma rays, Mount Jamar, I believe in the AGU, at Seminole, everywhere I've seen a spectral gamma ray, the thorium and potassium are extremely low, and the gamma ray is responding predominantly to uranium.
In terms of any actual logs in the EMSU, you have no spectral gamma to be able to make a differentiation between uranium, thorium, or potassium within the EMSU, do you?
No, but I have them
No.
outside it.
Now, you've talked about the gamma response, I think at where you would call the what you're now speaking to in terms of a impermeable barrier, the gamma kick.
I don't know if it's impermeable or not. I just see that that's a mappable high gamma ray marker that can be mapped across the entire EMSU.
Okay, so as we talk about that, the gamma ray kick that you've described that's mappable across, you shared before the break that you don't know where the Lovington sand is, you don't know what it is. It's not your testimony that that is an impermeable barrier, is that right?
Yeah, I don't know anything about the Lovington sand.
So just in terms of illustrating the gamma ray kick, did you hear Mr. Bailey's testimony about the Lovington sand is basically arcosic sands that have blown off of the ancestral Rocky Mountains and deposited at that location?
I've heard that testimony, yes.
That would be a shallow water environment, wouldn't it?
It would.
Okay, so we know that the Lovington sand would be shallow water environment. And you don't have any basis to disagree with Mr. Bailey's testimony about that coming from arcosic sands being blown off of the ancestral Rockies. Why would those have uranium in?
I don't agree with that. There's been work that's been done at Slaughter on the Lovington sand that shows that they're not arcosic at all, that the elevated uranium comes from organic matter.
Okay, wouldn't this be a question for a geologist?
I'm just reading what geologists say about the Lovington sand.
Okay, and you've heard Mr. Bailey's testimony in here. Would arcosic sand create a gamma ray response?
Arcosic sand would imply the presence of feldspathic input, so that would have radioactive potassium in them. What I'm telling you is that, and I was told that early on that was the theory about what was going on, but I've also done some research, and it's been determined, at least north of the MSU, that the elevated gamma ray is a result of the presence of organics in the what's called the Lovington sand. Now, I don't know if the Lovington sand makes it to the EMSU or not. I don't know.
Now, as we talk about the gamma ray marker in the EMSU, and if you just assume with me that the gamma ray is Lovington sand, is that basically where you change from a shallow water rock facies and then begin using a deep water rock facies?
That's not true at all.
Explain that.
I go from a predominantly shallow water environment above that due to the low gamma ray, typically low gamma ray. And then I go to a cyclic shallow to medium depth, back and forth with evaporite caps.
Is the gamma ray different above the Lovington sand versus below?
The value, if you draw a baseline through the minimum, yes, there's a shift below the Lovington sand.
Is it a significant shift?
Well, it's a significant in that if the response is predominantly dominated by uranium, which I believe it is, then that shift would indicate roughly 2 to 3 times the uranium content. And the uranium content of the ocean didn't magically increase below that marker. What happened below that marker was that the grain size, the average grain size of the material got smaller. And basically, the way it works out, a 3 times increase in uranium would imply about 1/3 the average grain size. And Lucia has shown that as the grain size mud content increases, the permeability goes down. And then if it's a 3 times increase in uranium, you would lose about an order of magnitude of permeability. So there would be a change in the rock behavior below that marker, in my opinion.
Okay, and the question was just, was it a significant change in the gamma ray? And I think after all that, the answer is it's not a significant
No,
change.
it is significant in that it would imply a major change in average grain size and a loss of permeability.
With respect to the change in rock facies, we've talked about the data that we don't have. Would you agree with me that you could at least be off by one level of rock facies instead of, agree with me that instead of mud dominated packed stone, or let me strike that, agree with me that instead of wax stone, this could be mud dominated packed stone?
Well, one, we don't have wax stone in the model at all. And two, that there's a spectrum of rock types between those that we model so that we can model the entire range that was present in the core data set. So for example, we could model between a mud dominated packed stone and a grain stone to determine a grain dominated packed stone. When the porosity starts increasing in the grain stones, the average porosity of a typical grain stone is 10 to 14%. When we start getting higher porosities, that is to indicate it's indicative of the presence of bugs. So we move from a grain stone to a molded grain stone.
The question was, would you agree with me that there's at least sufficient uncertainty here that you could be off on your facies by a magnitude of 1?
I don't know what that means.
For example, moving over from wax stone to mud dominated packed stone, could you be off by 1 facies? Is there enough uncertainty in the data to be off by 1?
Well, for one, there's no wax stone in the model. And two, there's a continuum between, so it wouldn't be a quantum jump from one to the next.
Would you agree that you could be off by approximately that magnitude if you want to average them over all of the depths?
I don't know, again, I don't know what that means because there's not one facies. I mean, it's not a quantum shift from one to the next. It's a transition from one to the next.
Could you, in terms of just moving from one to the next, could you be off by the next?
I suppose I could.
What does that do to your oil saturations in your model if you are off by one
Well,
magnitude?
again, it's not, the oil saturations aren't predicted based on discrete rock types. There's a spectrum of rock types between that sweep that entire range presented in the core data.
I'm going to try to work through these in order here. At your slide 2, you said you did review the facies descriptions from Dr. Lindsay?
As best we could. We didn't have a good picture of it. We tried and we could make out the facies. The problem that we had there was I had no idea what the resolutions were those. We built the model based on discrete core plug by core plug measurements tied back to the Lucia Cairns model. And I don't know whether Dr. Lindsay was describing individual core plugs or was he going up and down the core and describing what he saw at a different resolution. So so I don't know that there could certainly be a disconnect between a plug-based cross plot to determine a facies of a specific plug versus a general description of looking at the core and describing a depositional environment.
Do you agree with Dr. Lindsay that the San Andreas is high on the carbonate ramp?
The upper San Andreas probably is. The problem is you keep saying San Andreas, and it's not just the San Andreas. There's an upper San Andreas, and then there's a San Andreas deeper in the section that's below that gamma ray marker.
I'll indulge the difference that you're trying to draw here. The lower San Andreas, you disagree with Dr. Lindsay that would be high on the carbonate ramp, or you don't know.
The very upper part of that, where we have the high frequency sections, would be just at wave base and just below wave base, depending on where I am in the high frequency sequence. As I get deeper in the San Andreas, as I go below that high frequency interval, I'm getting increased mud content, which would indicate that I'm moving down the carbonate ramp more into the basin.
The question is, are you disagreeing with Dr. Lindsay that the lower San Andreas is high on the carbonate ramp, or is your answer, I don't know?
There's portions of it that are near wave base on the carbonate ramp. I guess you could say that would be high on the carbonate ramp. And there's portions of it that are in the deeper water portion of the carbonate.
And that's according to you in the lower San Andreas.
In the lower San Andreas.
How many feet of the lower San Andreas, according to you, are on the upper carbonate ramp?
In the lower San Andreas?
Yeah.
I haven't quantified it.
Talking in on the core earlier, before we broke, you said that you did depth shift the core. If you didn't have core gamma ray, on what basis did you shift the core?
Basically, we calculated the porosities using our porosity model, and then we looked at the core porosities and then moved the core sections up and down in order to get the core porosities to best match the log-derived porosities.
On your core oil saturations, did you come to the opinion here that a lot of the water was lost as a result of hydrocarbon expansion, dissolved gas?
Yes.
So if that water was lost because of dissolved gas, that means we have oil in that core, don't we?
Yes.
Do you agree that the adjustment would not be uniform from top to bottom and that you're going to have differences at different places in the core?
Yes.
Did you hold it constant or did you make adjustments throughout the core on the saturation correction?
We pretty much what we did is we determined an average value of the bleed factor and applied it throughout the animal.
I'm sorry. So was it held constant?
The bleed factor was the Bisabol, I think it was as well.
But you would agree for the commissioners that that would actually be, you would need variable corrections throughout the core.
Well, the interesting thing was when we went back and looked at the bleed that occurred at Maljamar, it was variable, but it wasn't uniform from top to bottom as you would expect. And what we found when we did the evaluation of the Maljamar core, in order to get the best match between what we would call corrected data, because basically with a pressure core, you can get an equivalent of what an uncorrected core would be. And because of the way they do the analysis, the bleed is quantified separately, and you can get I guess a mimicked picture of what a conventional core saturation would have looked like. Okay, and looking at that, you look up and down the core and you can see it's not exactly it. I think the average was about 19%. It wasn't necessarily 19% at every interval, but there wasn't a discrete trend noticed from top to bottom. And so the best match we got when we went back and practiced with the Maljamar data set was using the average. That gave us the least uncertainty between the corrected core saturations and the actual measured saturation. So we didn't see the variation that you're talking about when we were working with the Maljamar core. When we certainly checked for it, because I wanted to see, is there a depth related because in Maljamar, we went from the main production zone to the interval below the oil water contact. And I was curious whether I needed to change the bleed factor based on those factors. We saw that we didn't need to get the best match.
Okay, I'm not talking about a match. My question is, you would agree that the correction factor is going to be different as you move through the core. It's going to be different in different places. This is not a static. And in this particular case, you used a static one. You did not attempt to vary it. True?
That's true.
Thank you. Now, as we continue moving through, we're now at slide 5 of your presentation. Now you're talking about Guadalupe Mountain outcrop here, yes?
Mhm.
And so obviously this is weather exposed.
They dug down, if they actually described the process of peeling off the surface and getting down deep enough to try to get the interval where the weathering was not impacting the results. We're very careful about that.
But so you think that this outcrop study was not affected in any shape, form, or fashion by the weathering of the stone?
It was affected by the fact, again, they made every effort to get past the weathering layer, if you want to call it. There's a proper geologic term for that. I can't remember the name for it. But they dug down deep enough into the rock to convince themselves, at least, that they were below the interval with which weathering. However, they did point out, because of all the water that had gone through, that they could not quantify accurately the amount of anhydrite that may have been there originally. The other problem that you get to with outcrops is because of the ice fracturing, you can't really do accurate fracture analysis on an outcrop, and they didn't attempt to do so.
The permeability in the San Andreas here at EMSU is higher than the permeability that was measured at the Guadalupe outcrop, isn't it?
Not necessarily. These are average values, and if you go back and read the paper, you see that there's a range of permeabilities that were associated with each rock type, and these written here are the averages based on multiple samples of each rock type.
The averages in the San Andreas are above the average permeability reported at Guadalupe Mountain. Isn't that correct?
I don't know that that's correct. It really doesn't matter in the calibration procedure. The way that the cross plot is defined is it's divided into regions, and when the core permeable, the cross plot porosity permeability, it lands in a space, and that space defines the rock class or rock facies, not the specific point. For example, we didn't assign a 12% porosity and a 17 millidarcy permeability to the grainstones in our model at all. We just used the cross plot technique to identify the different facies present.
I'm moving now to slide 6. Here we have resistivity indexes on the y-axis and water saturation is the x-axis. Is that right?
That's correct.
What is the reference for the data used to make the critical water saturation lines?
It's in the paper. It's a Schlumberger model. And basically what you do is the process was this. I described it earlier. We identified based on the cross plot that was prepared from the outcrop, we identified the rock class or rock facies. We grouped the rock facies for a particular face. For example, let's just say grainstone. We grouped all the points that were identified on that cross plot analysis as grainstones, and then we plotted them on this plot. And then if you take that equation in the bottom left hand side of the figure and solve it for SC, you can get an SC value for each core point, and then we just average the SC values, and then we plotted that line as a function of saturation to make sure that it actually was a reasonable representative expression of the behavior of those points that were identified as grainstones.
So is the answer that this was not your data? This came from a Schlumberger reference?
No, this is the data from the EMSU. The model that describes it was developed by Schlumberger to handle this type of analysis for an oil bed carbonate.
The reference data. The reference data used to make the water saturation lines, is that reference data Schlumberger?
No, it's that data on that, the data on that cross plot is EMSU data from the core. The model, the equation at the bottom left, is based on a model developed by Schlumberger to handle oil wet reservoir. And it's in the references are in my testimony.
For, if we move over onto the right side, is the W, is that wax stone?
It is.
What is the water saturation there in your plot for wax stone?
In the plot, it'd probably be north of 90%. However, I'll remind you that wax stone wasn't included in our model.
What is your poorest rock then, if it's wax stone?
My dominated pack stone.
What is your water saturation for mud dominated pack stone?
Well, it's variable. You can see it varies depending on the resistivity index.
Up at the very top at 100%. I guess, do you know what the critical water saturation there would be?
100, that'd be 100 RI. There's not a percent.
Yeah, at 100 RI.
Oh, I have no idea what it would be. It doesn't matter what it is, a particular depth. It's the curve fit parameter that defines that curve. It's not a value at an RI. It's the curve fit parameter that describes the saturation found at each point on that curve. If I remember, I don't remember the exact number for that. That seemed like it's 0.78 or something like that. That's the exact number. But that 0.78 doesn't plot anywhere on there. The 0.78 is the parameter, the SC parameter that describes the curve that goes through those data points. And again, in the model, the SC is not a discrete value. There's a spectrum of them that exists all the way across there so that we can include all the different rock types in the analysis and we don't exclude anything.
And so each of the data point plots, explain what each plot is.
Okay, well, let's go to the grainstone. And what we should have done that we didn't, and it's because it would have been useless for me because I can't see it. But basically, the way the model was set up is we identified the rock class based on the Lucia Cairns model. We gathered all the rock for a particular class or facies. We gathered all the samples that were identified as that facies, and we plotted them on this cross plot to see where they fell. And then we fit a line through that data cloud based on the SC equation. Basically, what we wound up doing is calculating an SC for each one of those data points and then averaging it and then plotting that average SC back through this equation to see was it a reasonable representation of the data points from which it was derived.
I'm confident I didn't understand any of that. What I'm trying to understand, so if we have a dot that is on this, what is the dot?
It's a core point.
It's a core point measuring.
It's the water saturation from the core, and then the resistivity index calculated from the porosity of the core and the formation water resistivity, and the deep resistivity measurement recorded at the depth from which that core plug was recorded.
And you can tell the commissioners that there's a great deal of uncertainty in the water saturation correction on this plot. Isn't that right?
The water saturation correction? There's no water saturation correction.
None of this involves any corrections to water saturations?
It's the corrected water saturations from my analysis go into this, yes.
And there's a great deal of uncertainty in that correction to the water saturation from your analysis.
In my world, it was plus or minus 10%.
And that's off of the core, which.
Yes, that's based on my core analysis, my analysis of how to correct the core data.
With respect to the inputs on here, which of these are assumptions or something that you've corrected as opposed to actual data measured?
The porosity comes from the core. The resistivity comes from a measurement from the log. The assumption, the piece that where there would be some interpretation would be the water saturation. Because what I'm doing is I'm correcting the oil saturations to the best of my capabilities, and then saying the water saturation is 1 minus my corrected oil saturation.
If, using this plot, if I'm understanding it, at the, like the mud dominated pack stone,
Mhm.
if you make the decision that the facies here is mud dominated pack stone, what is the maximum amount of oil saturation that you could get into that particular rock facies?
It depends on what the maximum resistivity that exists, and I don't know what that is.
Is it less than 20%?
Oil saturation?
Yes.
It could be.
And
I
so
don't know. Like I say, it depends on where you are on that plot.
by merely selecting a facies of mud dominated pack stone, you can tell the commissioners that if you've selected that facies for a rock type, that can never have a amount of oil saturation that would exceed 20%. Isn't that?
I don't know if 20% is the right number, but that would be what the core data is telling us.
And again, I just want to, I'm trying to get this as simple as I can in my mind and maybe help some of the commissioners. By you selecting mud dominated pack stone here, based on your data throughout the entire San Andreas, if it's mud dominated pack stone based on that facies, it can never go over 20% residual oil saturation, can it?
I guess that would be true.
And we know that if it's less than, if it's 20% or less residual oil, you exclude all of those oil volumes from your oil in place summation, in this case, that you're offering the commissioners, correct?
If it's less than 20, we do.
And also in terms of Mr. Macbeth and his number, you know, he relies on your oil in place numbers, correct, for his
Yep.
opinions. And so here, simply by selecting a rock facies of mud dominated pack stone, we know from that point on, it can never have more than a 20% oil saturation. And we know that you credit none of those volumes for the purposes of Mr. Macbeth's economic work. True?
That's true, and that's based on Trenton's work.
And here we come back to the, as we talk about uncertainty, we do not have core through the San Andreas. We do not have pressure or sponge core in the San Andreas at EMSU. You're working off of a gamma ray. You don't have spectral gamma to be able to parse out thorium, uranium, and potassium. You would agree with me that there is at least one rock facies of variance possibility here based on your lack of data. For example, moving over from a mud dominated pack stone to a grain dominated pack stone.
Objection asked and answered.
Do you agree?
It's a long-winded sentence. Maybe you can break it into discrete questions.
But we've talked about the paucity of data here in terms of core. We have 0 spectral gamma in here. We have 0 sonic inside the EMSU. You're not a geologist, but we've heard from Dr. Lindsay, who is a geologist. What I'm coming back to is you would at least give me that with this paucity of data, it's possible that you would be off by 1 rock facies. For example, what you classify as mud dominated pack stone could be a grain dominated pack stone. True?
Suppose it's possible.
And at that point, the oil volumes here look much closer to the volumes that have been estimated by NewTek and by Exxon and by Ops Geologic. Isn't that right?
I disagree with those models are invalid. I don't agree with any of the saturations coming out with any of those models.
What were some of the N values that I'm going to jump here for a moment and try to find a slide that I think illustrates this better. Are you with me on slide 29?
I am.
EMSU, the red squares, will you tell the commissioners what the red squares represent?
Can you determine, Mr. Examiner,
objection, I guess. Dr. Davison is colorblind. So maybe we can figure out how to sort that out, but.
No, those are just differences between 679 and our Bell.
Okay, it's overruled, but, he, can you see, what, he's talking about, Doctor? The squares versus the,
Well, there's a legend in the upper right-hand corner.
Yeah, I didn't make the objection. I asked what the red squares are. I don't see anything that's not a red square on here. So, and additionally, he didn't have any problems testifying about the slide when Mr. Rankin had the mic.
okay, overruled, do your
No,
best, Doctor.
no, God damn it. Look, there's blue circles or something down at the bottom, and then there was red squares. There's both colors on there. And there's a label up in the right-hand corner explaining what they are.
And again, I didn't make, your lawyer made the objection.
Yeah.
I thought,
Yeah.
I thought you and I were tracking on red
Yeah.
squares.
I can't see the colors, but I'm guessing the colors, but I can see squares versus
All right.
circles.
So if we take the very upper left one, tell the commissioners what does that data plot represent?
That's a core point, and I guess that's a square, so that would be a core point from EMSU 679, where we took the porosity and the saturation and the resistivity values and backed out what an N value would be to make this water saturation that was measured, the corrected water saturation that was measured in that core match the core data. So in other words, we're going through Archie's law backwards, knowing the saturation, knowing the M value, knowing the RW, knowing the RT, and we're back and solving that equation for N to see what the N value would be. And this is based on what OPS did.
But you solved for this N value, didn't you?
From the core data using the procedure they gave us.
And weren't some of your N values here actually over 100? They were like 113 were some of your N values.
Yeah, and it could have been.
And Ops Geologic, they used a variable N as well, right?
This is the calibration procedure that they told me that they used.
My question is, it's just a yes or no. Did Ops Geologic use a variable N, yes or no?
Yes, they did.
And their variable Ns looked something from like 2.5 to maybe 9, 10 at some places, right?
Yeah, and it's that line that's fit through the bottom of the curve.
My question is your N values, some of those actually went as high as 113,
That's right.
which doesn't seem reasonable at all, does
It
it?
doesn't, but that's the point. This is using the calibration procedure that OPS said they used. And we went through exact same procedure, calculated N for each core point to try to figure out what they did. We took their model, which you're right, does have a variable M and N, and that came from the 746. We backed out what the N had to be for each of their saturations that they calculated, and then we plotted it, and it's a line on the bottom. So that what they did was they did exactly the same thing I did. They looked and they fit a line through the bottom part of the data to build their saturation model, their variable N model. And their variable N model is that bottom line. And my point is that bottom line represents the highest possible oil saturations for a given porosity, and it ignores about 80% of the actual core measurements.
So you built your own model and you came up with your own variable N values.
We didn't use N.
Well, you have to have an N in your equation.
No, we don't. The equation is the one that's on the bottom left-hand corner of that plot we were arguing about a while ago.
I've got a couple. This is going back to our slide 6, I think. What is the maximum oil saturation possible if SC is 0.78? And I can go back to 6 if you need to see
I
that.
have no idea. It depends on what the maximum RI would be.
What is the equivalent N for an SC of 0.78?
I have no idea. I'd have to calculate it. We didn't use Archie.
you understand that, that in their variable N, Ops Geologic made adjustments to to their core analysis, right?
I don't know that they made, I know that they used a model to calculate the correction factor to correct the raw measurements to what they considered as the corrected measure.
As there's measured oil saturation in the core, would you expect the lower oil saturations to be closer to accurate or the higher oil saturations to be closer to accurate?
I don't have any idea which ones are more accurate. Bleeding occurs from all of them. It's proportional to the amount of gas that's in the oil and the viscosity of the oil. So the relative bleed is probably relatively simple. It depends. For example, if a core has 1% oil, it's not going to bleed as much as a core that has 50% oil, simply because it's an expansion. It's an expansion based on the amount of oil that's originally left in the core. So there's not more bleed at one level than the other, unless there's more oil at one level than the other.
As we come back to get to the right slide here. With respect to the porosities and permeabilities, you've seen that numerous RAWs discussion that oftentimes the highest oil saturations will in fact be found in the lower porosity, lower permeability rock.
Well, that could be the case if it was originally filled with oil and then displaced. For example, at Seminole, the theory is that there was an oil column there, and then there was a trap breach. The oil water contact moved up and displaced oil out. And if you go back to if that were the case, you could go back and look and see that the saturations would be expected to, in that condition, be somewhere in the 20 to 40% range. And the 40% can be associated with some of the good rock, and it can be associated with some of the poor quality rock.
I want to put up a paper to see if you're familiar with this paper. This is Journal of Petroleum Science and Engineering by Bo Wren and Ian Duncan. Have you seen this paper before?
I have not.
I'm going to get down to section 4. Is that large enough for you to read it?
If you just tell me what you want me to answer.
They say this study has not attempted to specifically model the Seminole field. Rather, we have modeled the formation of a generic ROZ by starting with an oil saturated reservoir. Its thickness is equivalent to the sum of the current SSAU ROZ and producing MPZ. Our simulations reproduce many of the features reported from the San Andres ROZ. The simulation results are consistent with an effectively steady state being reached, at least with respect to oil saturation, on a time scale of 50,000 years. It is significant that even after 1 million years of regional water flush, the oil saturation in several patches remains similar to the initialized values, 0.7 to 0.8. These patches are local areas of lower porosity and permeability. This observation is consistent with the observed presence of oil stains in the less permeable patches of the San Andres core samples. You would give me that there is literature that would document the ops geologic conclusions that oftentimes some of the best oil, residual oil saturations are actually found in the low porosity, low permeability rock.
I wouldn't agree with that because it's based on model results. And I would add that our model did a reasonable job of reproducing what they actually saw in the core measurements from SSAU.
I intended to ask this earlier and I forgot. On the core oil saturations and your analysis there, what was the pressure in the San Andreas?
Well, we modeled a range and it was based on the available MDT data. It prior to the start of the water flood, I believe the lowest pressure that we had was about 365 PSI. And then we've argued about this point is whether it's San Andreas or Graybird or whatever, but I think the highest pressure in that interval was about 1264. If we go back and look at what would the pressure be in the San Andreas had there been no withdrawal at all, it seemed to me like it's about 1700 PSI, assuming it wasn't under pressure. So we modeled, when I did the modeling, we modeled that entire range. I said, well, what if the 679 core had been depleted all the way down to 350? What would my viscosity, B sub O, bleed be? Then I modeled all the way through that entire range, all the way up to this, assuming there'd been no pressure depletion at all at the EMSU 679, which is not practical because it's up in the just below the producing oil water contact you'd expect. At least there'd be some. Now, if you go back and you look at, I believe it's the 211 data where all these MDT measurements were made. It's roughly the same depth equivalent to the 679 core. So it seems to me that the pressure range of 1265 to 364 would be a valid range. So that's where we did most of our analysis. So when we calculated the bleed and the expansion and all the factors that go into that correction factor, we modeled it over a range from the 365 to the 1264 PSI. And then just for an upside, because I was been bugged on you guys aren't including uncertainty, I went ahead and modeled the point, assuming that there'd been no pressure drop at all at the 679, which is 1,700 pounds. So then we derived a range of potential correction factors for each one of those conditions based on the B sub O, the gas content, and the viscosity that were associated with each one of those pressures. And then we got a range of the final correction factor from 1.1 to 1.25 for the condition where we said 1265 is the maximum pressure it could be. But if we assume there'd been no depletion at all, it gave us the 1.3 correction factor. Once you reduce the reservoir pressure and gas bleeds out of the oil, you don't get to go back and use the original B sub O to do your calculations, which I think a lot of people do, and that's an error.
You know, I'm trying to get this thing's not sharing. All of a sudden, I'm having your problem. Trying to get a slide to share here. There you go. All right. I'm going to try to use these slides to illustrate. As we talk about just your model and how do I get this to play? what I've endeavored to do here is illustrate your cutoffs. In terms of your volumes, do I have this correct? That, for example, if we're looking at effective porosity on the bottom X, that if you get below 0.1, I'm sorry, 0.7, at that point, is this correctly illustrating that you would give zero oil volumes to anything below that 7% effective porosity?
Conclude that below 7% is non-reservoir rock, and we don't do any additional evaluation beyond that.
Okay. If we, and now I'm showing an osteologic prepared slide to just illustrate in terms of plotting against the core measurements from the 679, the RR Bell, the 458, and the North Monument. Do you see at 0.7 effective porosity, we've placed a dashed line that goes up that's on the x-axis between the 6 and the 8?
I can't see it, but go ahead.
Well, I want to make sure you can see it because I want to bring it back to just show the commissioners graphically kind of what we're talking about here by way of volumes. So can you see the cursor at least?
Yeah, I can see it sort of.
Okay, the cursor's at 7% porosity.
Right.
And that would be where you cut off, yes?
Uh-huh.
If we move over to the left at 4% porosity, this would be the osteologic cutoff, right?
Right.
And then on the y-axis, do you see the permeability of 0.1?
Right.
And you're saying you did not cut that off at 0.1, or you did?
Well, basically what we did, we plotted, I think, the cross plot's in my testimony. You can see what we did. It's one of the attachments of my original testimony. We cross plotted the core data from 679, and then we fit a line to it. And then we selected 1 millidarcy, 0.1 millidarcy, read over to the right, saw where the regression line was, read down, and picked 7% cutoff. And at that level, the way that we've drawn it, we'd be excluding as many points that were permeability above 0.1 as we would be including that were below. And that's, typically in the San Andres, a 0.1 millidarcy is chosen, and most operators use cutoffs in the 6 to 8 PU range. It's pretty standard in the San Andres. That's what people do to calculate pay.
Earlier, we were talking about the core corrections and N values. And what I'm trying to do here is graphically illustrate. You would agree that the core has to be corrected. The core volumes of oil saturation have to be corrected, right?
Yes.
And the correction here that Opsgeologic performed needed larger corrections down at the lower volumes of oil measured in core, smaller corrections up at the higher saturations of oil in
I
core.
don't believe that that's what was in their write-up. They basically said they used a rule of thumb based on a paper that was published, and I've got the same paper, and used that correction in order to do it. In my view, it was one number. If it's not one number, that's not what Mr. Burke had stated in his write-up. And then he basically said their low side was based on uncorrected measurements, and their high side was based on a correction based on a rule of thumb that came out of the paper. I may have that wrong, but that's what I understood.
And here, this is just a modification slide you had earlier. This is basically Opsgeologic demonstrating that if you're not filtering out the poor, the questionable data, you're going to have those unreasonable N values that would get up into the 100 plus.
And we didn't use those for anything in our analysis. What I was trying to understand is how they calibrated their model. And I see how the model, and if that thing that has 3 lines on it is their model, then fine, they still are excluding measurements from probably more than half of the core. There's nothing magical about our points. We're just plotting the core data in terms of N that comes from backing N out of what it takes to match the core measurements.
And again, what do your N values look like in your equation? I understand that you didn't come up with your own N, but in your equation, what did the N's end up at?
I don't know. I'd have to calculate them because we didn't use N in our model. We used SC in our model. So for each point, I could calculate an N, but that would only correspond to that RI and that porosity and that saturation. If I moved a foot down, even though I was in the same rock type, I would have a different N, but I'd be on the same SC value. That's the beauty of that model, is I can characterize a variable N for all practical purposes with one curve fit. And it is possible, I guess, you could go through and then calculate an N for each one. We didn't bother to do it because we didn't use an Archie model.
Do you know approximately what N's would have been calculated? I hear you on your SC.
Yeah.
Do you know about what the N's
They
would
would
have been?
probably have been, I don't know, 6 to 10, 6 to 20. I don't know. I didn't do the calculation. I'm just speculating on gut feel.
Go back to your presentation. With respect to the residual oil saturations that you're reflecting here in slide 10, what will you just explain for grainstone, molded grainstone, grain dominated packstone? What are you demonstrating with this slide?
I'm just showing, based on the measurements that the Bureau of Economic Geology made, I think some of these were outcrop cores, some of them were Seminole San Andres cores. There's a variety of sources for those, but these are average residual oil saturations to water that were reported for the rock types. And I'd point out that, you say, well, you're assigning something and therefore you're limiting it. I would point out that when we take our model and apply it at SSIU in the ROZ, we can reproduce this range of residual oil saturation. So the model will work and provide the right outputs. And obviously we're picking facies in the model, and we've been able to verify it at Seminole. We've been able to verify it at Tall Cotton. We've been able to verify it at Maljabar.
And I guess what I'm trying to understand is that it's been the testimony of Goodnight in this case that the San Andres is an ideal place to inject salt water. And in looking at the facies that you've actually selected for the San Andres and the water, the critical water saturations that would be in there, maybe this slide, your slide 6 helps illustrate it, but how on earth could you move water through that if your facies are correct and the water saturations are as high as you've represented in your testimony to the commissioners?
San Andres is full of cars.
So your explanation for these rock types and the critical water saturations that you come up in these water saturations you're up to are over 90% in the majority of the San Andres, isn't it?
No. Well, there's places where there are what I would call migration paths where that's not true. I don't know that San Andreas ever had any. The point is the matrix of the rock in the San Andreas would be relatively poor compared to the better quality rock up in the Grayburg. What makes the injectivity so high is the fact that we've had the sulfuric acid going back and forth through there in the multiple meteoric paths of pore volumes of meteoric water going through.
So ignore the water saturations and the critical water saturation that you've come up with, and ignore the facies that you've assigned to these rock types. Your explanation for why the Goodnight is able to inject into this is all on karsting as opposed to the rock type.
I think so. I think the karsting is the major component of why we're able to, however, the rock, the permeability, it's like I said, the increased gamma ray content indicates an increased mud content, which indicates indirectly poorer permeability. So the rock type, and there are high permeable grainstones in there. It's not that I've excluded grainstones and mud dominated grainstones from the lower San Andreas. They're there. All rock types are there. As you move deeper in the system, you get more and more of the poorer quality rock types, and they're not going to, they calculate as having very high water saturations. So my conclusion is there's not a lot of ROZ down there or any at all. It's probably migration paths, and the injectivity that they're getting has to do with the karsting.
So again, I'm just trying to figure out with my simple mind how two of these things can be at the same time. How is this rock type, which you've selected, being either non-reservoir? Is non-reservoir even worse than waxstone, right?
We don't have waxstone in the model, but the non-reservoir would be the lower than 7% in the mudstones, the lime mudstones.
Okay, what's your the non-reservoir? Is it between waxstone and mud dominated packstone, or is it on the other side of waxstone?
Non-reservoir is anything under 7%, basically.
Okay. Under 7% effective porosity.
Yes.
And so, and you've chosen that facies for the vast majority of the lower San Andreas, upper San Andreas, all of it, haven't you?
I don't know that that's true.
How do you not, if it's your facies, how do you not know what rock is in your own model?
Well, we can see that there's grainstones and mud dominated grainstones, or we wouldn't have, that's where the oil saturations are. When we get into the high gamma ray stuff, that's poor quality rock, and that's going to be those poor facies.
And isn't that, according to you, the vast majority of the lower San Andreas?
I don't know if it's the vast majority. It's certainly a good swath of the interval where you have high gamma ray that appear to me to be almost a carbonate shale.
My question, isn't the vast majority of the lower San Andreas, according to you, the non-reservoir rock?
I don't believe that's true. I believe I'm calculating those low saturations in the vast majority of it. I don't know what the highest or what the major the distribution of rock types in the lower San Andreas. Again, we didn't put out rock type curves, so we didn't do analysis on that.
So the very first batch of questions I asked you was that your model is very facies dependent. It comes down to the rock facies that you assign and that you pick for the lower San Andreas.
Yeah,
we talked about that.
That's true, but
And I'm asking,
I could get a grainstone and a very low RI and calculate a high saturation in a grainstone. And that's the best facies.
Your model is very facies dependent and facies specific based on what you pick.
It's also resistivity dependent.
Now, in the lower San Andreas, the vast majority of what you pick in the facies is non-reservoir, or you don't even know.
I don't know what the vast majority is.
How can it be that the facies is so poor that it's lacks such permeability and lacks such porosity that you're calling it non-reservoir, but it is, and you've got it at nearly 100% critical water in some places, but it is so ideal for injecting salt water.
Because there's karst.
How can those two things exist at the same time?
Okay, if you look at where the karst are, they're in the high porosity intervals with low resistivities. And so what's happening is water's moving through there, and what we're doing is we're creating bugs, and we're connecting bugs. The bugs can be present in any of those lithologies. And with the long-term passage of the meteoric water and the H2S, sulfuric acid, I'm creating permeability due to dissolution. And that occurred over long periods of time. If you look where the EMSU is, it sits right on top of what Trentham and Melzer have described as the Artesia Fairway and the Capitan Fairway. Those two fairways coming together have pumped a bunch of water through there. And if Lindsay's right, and we had counterflow of H2S at the same time we had meteoric water, we put sulfuric acid through that thing multiple times, maybe up to 20 times. And that's going to create the karsting system. And that's why it's different. This thing is karsted to heck below that marker, but it's a different karst style than exists above the gamma ray marker.
You just mentioned vugs. As I understand, vugs are critters, fossils, that type of thing.
No, it's where you've dissolved out a critter or fossil and created a void in the rock.
And that happens at a surface. Yes,
No.
a shallow water environment.
No, it doesn't. It can happen anywhere. Happen anywhere that acidic waters move through. And that's the whole point. The acidic waters in the Trentham Melzer, and I'll say Alton Brown model, multiple pore volumes have been through there, and it was after the whole San Andreas interval was uplifted and water came through. So it wasn't depositional. The creation of the bugs in the water disposal interval occurred way after deposition, after the uplift of the Guadalupe Mountains and the exposure of the San Andreas to meteoric fluid input. So it's a totally different system. It's not a shallow water environment.
I'm going to move over and now talk about your idea of impermeable barriers. First, what's the difference between a baffle and a barrier?
I don't, well, ops described their low permeability, low porosity zones as baffles, which implies that they don't aerially go very far. A barrier would be one that would exist where you could map over long distances.
Okay, well, I'm thinking of a baffle like in a truck, like a milk truck or a fuel truck. You're familiar with like a baffled truck that's moving liquids?
I have no idea what you're talking about now.
Baffles do not stop flow. What a baffle would do would inhibit, slow, impede flow.
Yes.
Okay, and so you appreciate that there is a difference between a baffle and a barrier.
Yeah.
Agree? Now, in terms of I was reading your SIR rebuttal, and nowhere in there do you actually say that it is your opinion that there is an effective barrier across the EMSU. It is not the opinion of Netherlands Sewell to this New Mexico Oil Conservation Commission that there is an impermeable barrier all the way across the EMSU between the Grayburg and the San Andreas, is it?
My testimony is as a result of the anhydrite layers that exist in that yellow highlighted interval, that the injection that is occurring below that yellow highlighted interval is isolated from the production that is occurring above that yellow highlighted interval.
Let's take the highlighted interval. I would just like Netherlands Sewell to be on the record. Are you here under oath testifying for Netherlands Sewell that the yellow highlighted area, since we can't speak of Grayburg and San Andreas, and you don't know where the Lovington Sand is it the testimony of Netherlands Sewell here? Are you swearing that there is a impermeable barrier across the EMSU at the yellow highlighted area? Yes or no?
I'm swearing that there's likely no communication through that yellow interval.
So if Mr. Rankin wants you to swear to this OCC that the yellow area here is a impermeable barrier, no fluid shall pass across the EMSU for Netherlands Sewell, are you swearing to the OCC to that or not?
We haven't seen evidence that there's been water movement from the injection zone into the MSU.
Is your answer that you're unable to swear one way or another?
I guess that's true, but that we haven't seen evidence of movement, even though 120,000 a day is going into that interval below. We haven't seen evidence that it's penetrated above that yellow interval.
And so again, so that I've got one question on this. One question and answer. Your testimony for Netherlands Sewell, you are
The
not,
testimony's not for Nellen Sewell. The testimony's for me.
Doctor, wait for the question. I know you can anticipate it, but remember the poor, long-suffering court reporter.
all of the revenue that Mr. Rankin or his client are paying is not going to Dr. Davidson. It's going to Netherlands Sewell here, yes?
That's correct.
Netherlands Sewell is the firm engaged as part of this case, isn't that right?
I'm engaged as the expert in this case.
As an employee of Netherlands Sewell.
Correct.
If the commission wants to know what the testimony of you for Netherlands Sewell is as to impermeable barrier at the yellow area from your demonstrative slide 17, you cannot testify one way or the other as to whether that is in fact an impermeable barrier all the way across the EMSU that does not allow fluid to pass.
I
True.
cannot, but I can say that the
Object
evidence,
to the non-responsive after that.
no, I can say that the evidence indicates that it is.
Object to the non-responsive after it is not.
Doctor, it sounded to me like a yes or no question. You'll have a chance to explain your answer on redirect if Mr. Rankin goes there.
And he's
So-
got my answer.
It is not your testimony. True.
Mr. Hearing Officer, it's getting a little heated right at the moment. I think we should probably take a short break, about 15 minutes. And I want to remind everybody, decorum. I have said this multiple times. We're not going to accept anything else but decorum. So everybody needs to be on their best behavior. So, Mr. Hearing Officer, let's take a 15-minute break.
Okay, that's great. Let's call it 2:40 and be back at 2:55.
Thank you.
On, there we go. Okay. Ms. Apodaca, are you ready in the back?
Yes, we're ready.
All right. And Madam Court Reporter, are we back on the record?
Yes, we're on the record.
Okay, thank you. I'll just remind council and Dr. Davidson, try to remember to wait for the end of the question and answer before speaking again. Think of it like a radio transmission where people say over at the end of the presentation without the need to say over. Thanks. Go ahead, Mr. Waymire.
Thank you. I think I have less than 5 or 6 minutes of questions here. Based on the last answer that I got. On the geomechanical studies, are you aware of any geomechanical studies that Goodnight would have performed before commencing saltwater injection into Empire's oil unit?
I'm not.
With respect to the frac gradient, in any frac gradient studies, that is, at what pressure will existing fractures expand? Any frac gradient studies?
Not aware of any.
Do you agree that there would be a ROS in the upper San Andres?
Could be.
Are you aware that Goodnight's Rhino well is injecting into the upper San Andres, has perforations and injects into the upper San Andres?
I'm not aware of that.
And then these are two cleanups. How did you calculate the resistivity of the water?
We use picket plot analysis.
And at slide 6 that I'm publishing right now, we've talked, did you made corrections to the data that's plotted on here?
To the,
Yeah, what the data plots?
those are corrected water, those are water saturations based on corrected oil saturation.
That you prepared?
Yes.
And so as we try to get back to your N, do you see that there are two curves drawn through the graph? One is an N of 2, one is an N of 3.4.
Yeah, but those are just for display purposes. We did not use those.
But as we talk about where N would be drawn through your plot, that would obviously be farther to the right, would be a significantly higher N, wouldn't it?
If we had used N, it would be. We didn't use N.
I understand you're saying you didn't use N, but we can see where N would be based
Yeah,
on
it
your
would be
work.
higher than the 3.4.
Can you just eyeball this? What about would N be based on your work?
Where?
How about for a grain dominated pack stone?
I have no idea. It looks like, if I just had to pull a number out, speculating, and grain down, that might be 6.
How about for a mud dominated pack stone?
And maybe an 8. I don't know. Again, I could calculate for each one, but we didn't use it, so I didn't bother to go through that analysis.
And what would N be for a wax stone off of here, just eyeballing it?
I don't know, maybe 10. Higher.
I'll pass witness.
Okay, Mr. Moander, cross-examination for
Yeah.
OCD.
I do indeed, Mr. Hearing Officer. Thank you. Good afternoon, Dr. Davidson. This shouldn't take us very long unless you shock me here. So you were deposed in this case, is that correct?
I was.
And you also submitted a rebuttal testimony in this matter on behalf of Goodnight, correct?
That's correct.
And in your deposition, you had testified that you didn't have any opinions on communication between the San Andres, to the Hobbs Channel, to the Capitan Reef. Is it still the case you don't have opinions on that issue?
Well, I guess based on what I've learned, my opinion now with the water would most likely move to the east rather than to the west, but that's based on what I've heard and getting a little bit better understanding of the Trentham and Melzer model and the implications of the potential oil and water withdrawals from the central part of the Central Basin Platform. Yeah, again, this is simply an opinion, but my opinion would be the water would more likely move to the east than to the west.
And you'd agree with me then that this is a new opinion not previously disclosed in any filings or during your deposition?
That's correct.
All right. And then as to the particulars of your opinion, so what you're testifying to is, if I understand it correctly, is, well, actually, what was the basis for this new opinion factually?
Again, as I've learned a little bit more about the Trent M. Melzer theory and revisited some of the work that ARCO did back in the early 90s, there was a establishment of tilted oil water contacts in the middle of the Central Basin Platform, which in the tilted oil water contacts would imply a hydrodynamic gradient across the Central Basin Platform. And since that time, I've gone and looked at the withdrawals that occurred. And again, before water flood and CO2 started in earnest on the top of the Central Basin Platform, roughly 7 billion barrels of oil had been produced, and who knows how much water had been produced from the central part of the Central Basin Platform. And given that the Trent M. Melzer theory would connect the water in southeast New Mexico to the Central Basin Platform, it makes sense that those tilted oil water contacts become a little bit more credible to believe that maybe they do exist, and that would imply the movement of pretty large volumes of water from New Mexico into the Central Basin Platform in Texas. Again, this is all opinion. I haven't done, I'll tell you right now, I haven't done the hydrodynamic studies, and I wouldn't even begin to try to do something like that. However, I understand that Bob Trenham did do quite a bit of hydrodynamic work and concluded that quite a bit of water had moved across it. I think in his world, something about 15 to 24 volumes of water had moved out of New Mexico and into the Central Basin Platform. So if that's consistent and the tilted water contacts are consistent, it would suggest that water is moving from west to east. But again, am I an expert in that? I am not. Have I done the hydrodynamic work? I have not. That's simply an opinion based on preponderance of the data I've looked at.
And do you base this opinion on your background with knowledge, skill, experience, training, and education?
That's correct.
Okay. Mr. Hearing Officer, I'm going to go ahead and move to strike this opinion, since this was absolutely not disclosed in any way, shape, or form. I fleshed out that this has been developed outside the various deadlines in this case. This is 100% ambush testimony, which I am not in a position to refute at this point or cross-examine effectively upon.
Mr. Rankin.
Well, I guess my understanding is Dr. Davison was asked a question and he listened to all the testimony during this hearing and did some additional investigation. It wasn't within his scope of what we asked him to look at. And so there are other witnesses who will be testifying on the questions that Mr. Morander is asking. So I don't have an objection to striking the testimony. However, I understand it is based on everything that Dr. Davison has reviewed or listened to today to this point.
Okay, well, this is a bit of a difficult ruling. On the one hand, Mr. Moander, you asked a question, you got the answer. On the other hand, the witness has said he's not an expert in this field. So it seems to me that the opinion that he gave at least deserves little weight. I'm not inclined to strike it entirely. We can't unring the bell. What's been heard is what's been heard, but I think the commission can take into consideration that Dr. Davidson has self-admitted that this is just basically a lay witness opinion in an area calling for expertise that he lacks.
Well, that's fine. I can ask him some other questions and we'll suss this out a little further then.
All right.
So Dr. Davidson, give me one moment here. So you'd agree with me, you were deposed in this case on November 22nd, 2024?
Yes.
And at that time, you were to render your opinions from examination from the parties opposing Goodnight. Is that your understanding?
Yes.
Do you recall testifying when you were asked specifically by me whether you had any opinions on the existence of migration of injection fluids in the San Andres into the Hobbs Channel to the Capitan Reef? You recall that question?
I do.
And then you answered, I haven't looked at any of that. You know, that's more of a geologist bailiwick than it would be for me. And we have not looked at, in fact, I haven't looked at any of the wells. I assume from what little I do know, that would be to the east, or excuse me, to the west of the MSU. And I haven't looked at any of the data from that direction. That was your answer?
That's correct.
And then let me share a little something here. Up. All right, Doctor, you recognize this document? Let me zoom in for you. My apologies, I forgot.
Yeah, that's my self-affirmed statement.
Okay, more importantly, this is your self-affirmed rebuttal statement, correct?
Right.
Is that right?
That's correct.
And could you point to me in here where you recite anything you just told the commission about your opinion on migration from the San Andres?
It's not in there.
All right, thank you. All right, turning back to your prior testimony. At that same deposition, do you recall that you testified you had no opinions on the broad scale impacts of injection into the San Andres?
That's correct.
And you also testified that you had no opinions on the effects of subsidence in relation into injection into the San Andres?
That's correct.
And you also testified that you have no opinions on seismicity related to the injection at issue.
That's correct.
And I've got to ask this since we've got a changed opinion here. Have you altered your opinions on any of these three topics since you gave that testimony and or filed your rebuttal testimony?
I have not.
All right. With that, Mr. Hearing Officer, I'll go ahead and I will pass the witness over to Mr. Beck.
Thank you, Mr. Moander. Mr. Beck for Rice Operating.
No questions. Thank you.
I assume that it's Mr. Suazo for Pilot Water Solutions.
Correct. Pilot has no questions.
All right. Instinct tells me that Dr. Ampoma may have some questions. I'll turn it to you first, Dr. Ampoma.
Thank you, Dr. Davidson, for your testimony. I just want to clear this. So are you a petrophysicist or you are engineer? Just for my own clarity.
I do both. My PhD is in petroleum engineering. I specialize in petrophysics and reservoir description for modeling.
So, you know, let's say within the petroleum engineering discipline, you have a lot of expertise in formation evaluation specifically.
Yes.
Okay. I do have a couple of questions, so I'll try to go through that as quickly as I can. You showed And if we can bring up the slides that you went through, that would be much helpful. Now, you showed a depositional environment, and I want to know, is this one for, so that would be slide number 2. Will this one be for the San Andres?
It could be for either one, but because the depositional environment is the same in the Grayburg and San Andres. It's just that the Grayburg that has spent more time in the high energy environment than it has the low energy environment.
Okay, let's go to slide number 3. Okay. So did you use a constant BO for the estimation of the correction factor?
Well, again, I estimated a range of correction factors based on my assumption of what the lowest reservoir pressure that had been obtained before the core was cut. But when I used a constant BO from the top of the core to the base of the core, but then I estimated a range of pressure, so there were actually a range of BO values. At the end of the day, I used an average correction factor that was kind of in the middle of the range that based on the uncertainty in the pressure range that existed for the pressure that was the lowest pressure that it would have existed at the coring location at the time of the core.
So was the correction applied to the core measurements?
Yes.
Now, as you look at multiple conditions or situation at which there could be oil losses during coring. Now, and based on all the discussion that we've had today, at least based on your testimony, do you believe that the oil saturation that has been calculated or more or less even from the core analysis could be underestimated?
Well, the analysis I did, I tried to include all the variables that would be involved in that correction factor, and I came up with a range. And again, the range that I came up with was about 1.1 to 1.3 correction factor, depending on the assumptions on how low the pressure had gotten. I settled for, I think, a 1.22 correction, which was kind of in the middle of that range. And then, however, if the reservoir pressure had not significantly fallen from original conditions, the correction factor could be quite a bit, could be the 1.3. And I testified earlier that would result in about a 10% increase in the saturations. For example, if I had calculated a 20% oil saturation, then, if the pressure had not fallen as low as I thought it did, that it could be a 22% oil saturation.
Now you talk about, so right on your point 2, number 2, you talk about just getting to the end of the sentence, a pore volume reduction to account for reservoir stress condition. Can you discuss a little bit about the reservoir stress condition you are referring to here?
Yeah, what I did is I went back and looked at a range of I calculated pore volume compressibility for a range of pressure drawdowns. And then it turns out it's a very insignificant number, but basically I said, well, if the reservoir pressure had fallen to 300 pounds, what would the net effective stress be? And then I used the net effective stress in a model that we use internally at Dell and Sewell to estimate what the pore volume compressibility was. And then after I knew the estimated pore volume compressibility, I estimated how much the pore volume would have contracted as a result of the net effective stress. And I did that for the full pressure range that I looked at. And in fact, they turned out to be relatively insignificant values, but I wanted to include all the possible mechanisms that would change the oil saturation when I did the analysis.
You made mention of the pressure reduction. So did you see any pressure reduction in the San Andres?
Well, the core, again, now these are just the corrections that I applied on the 679 core. And the problem is I don't know for certain what the lowest reservoir pressure that was seen in the area that was cored prior to the coring operation was how far had the reservoir pressure been drawn down. I did have some from, I think it's the MSU 211, there were some MDT measurements at roughly the same depth, and there was the range of pressures that were exhibited in that MDT, I think were 367 to 1264. I may have those numbers wrong, but I ran that full spectrum of possible lowest bottom hole pressures and then calculated the B sub O, the R sub S, the viscosity, and then the correction factors for each one of those conditions. And that's where I came up with a range of a correction factor of 1.1 to 1.3 or 1.25. Again, if I assume that there was absolutely no pressure drop in the San Andres, that whole core was at initial reservoir pressure and it had never been depleted, I get a 1.3 correction factor. So that's the range of correction factors given the in situ conditions of the oil at the time that well was performed, or the potential conditions that could be present at that location.
So you said you looked at various ranges of pressures.
Yes.
Now, let me ask you, so in your estimation, what is the initial reservoir pressure within the San Andres?
Well, I would assume it would be at a hydrostatic gradient. I think that turns I haven't got the numbers in front of me. It seemed like it was about 1700 PSI if I assume that the San Andres had never been depleted and it was at a normal hydrostatic gradient.
So then it is your testimony that the San Andres is not under pressure.
I think the San Andres is under pressured. For example, I think if I remember right, and I may have these numbers wrong, but I think the gradient that they're measuring in the injection zones is roughly about 0.38. If it were not under pressured or somewhat depleted, I think that number would be more like 0.43 or 0.44, somewhere in that range. So, and I don't know what the problem is. I'm not sure anybody knows what the initial pressure in the San Andres was before any of these fields were put on production. Whether it was under pressure or not, I don't see a reason it would be under pressure, but maybe it was.
Dr. Davidson, I asked you about what the initial pressure in the San Andres was based on your analysis, because you talk about you looked at multiple pressure ranges, and then you told the commission that it is hydrostatic, which is about 0.4344, 1700. Now, and I asked you, is the San Andres under pressure? And then you are saying yes, so I'm confused. Well, can you help me out?
The current measurements, I mean, the press of what was purported to be the upper San Andres in the MDT measurements. And again, I don't know where the top of the San Andres is, so I don't know. I'm just going based on what was put forward by Empire. The San Andres interval would have had about a 1264 PSI pressure. That would be under pressure. They attribute that pressure as being evidence of flow from the San Andres into the Grayburg. Now, the other piece of information that I'm aware of is that the injection, the gradients in the injection interval, that disposal interval, which is below that yellow band that you see on this figure, if we go down into the what I'm calling the lower San Andres, which exists below that yellow band, the pressure gradient there today is, I think, about 0.38. In my view, that would indicate that the lower San Andres is under pressure. But what I don't know is it always been under pressure? What was it in 1934, 21, before any of the production started? I don't know what that pressure was.
Well, Dr. Davidson, then my question to you is, do you believe that there is an uncertainty associated with even the correction factor that you calculated?
Well, the correction factor I calculated used the nearest pressure measurements to that well that I had at the time. And at that time, my conclusion would be that the San Andres around that well would have been at a pressure somewhere between 364 and 1265, or whatever, that somewhere in that range, because that's the pressure measurements from the MDTs that I had available to me at about the depth of the core, at about just before water flood and operation started. And the BSABO and all that needs to be calculated at the lowest pressure that it was obtained prior to the initiation of the water flood, because the water flood has the potential of repressuring the reservoir. I don't know if it did, but it has the potential of repressuring, but you can't put the gas back in the oil once it's escaped. So you need to know what the lowest pressure was prior to the initiation of the water flood at about the depth at which the core was recorded, and there was a range of pressures that were available. So I evaluated the full range, and those ranges would indicate that that part of the San Andres and Grayburg were reduced pressure from a hydrostatic conditions.
So you utilize the same correction factor for the Greenberg and then the San Andres?
I used the average through that whole interval because I couldn't tell for sure what the actual pressure to use. What was the proper pressure? It was somewhere between 364 and 1265. So I evaluated the full range, but for the corrections, I used something that was roughly in the middle of that range. And you know, the fact was this evaluation of the what the correction factor occurred after the fact, that after I'd already done the original calculations. The original calculations were carried out using an ARCO oil and gas company research rule of thumb that I had used back in the early 80s when we were evaluating core data to evaluate potential CO2 floods. That number from that analysis came out as 1.22. If I take the average of all the measurements that I made from the 365 to 1264, you come up with 1.22. So I'm like, gosh, no matter what I do, I'm coming up with somewhere in that range. So I didn't go and change all of my corrections. I just said, well, my original correction seems to be in the right range. And that would be somewhere average between 365 and 1264, maybe 1,000 pounds or so would be that average that I assumed would have existed, the lowest pressure that existed in that core area prior to the drilling of the core.
Dr. Davidson, so are you telling the commission that the correction factor that you actually used was based on your experience?
That's correct.
And not necessarily based on the actual data from the San Andres EMSU?
Well, it was from the Grayburg San Andres pressure measurements. What I did was, because there was concern voiced by Empire that was a very simplistic way to do the corrections. I went and did a full rigorous evaluation of what the possible range of those correction factors could be. And that the evaluation of that full range came out to be 1.1. And if I assumed absolutely no pressure drawdown at all, the 1.3. And so the point is, I saw no reason to go back and change anything. Then when pressed on, well, what's the uncertainty? Well, I followed the ops model, and what ops did is they decided that the biggest uncertainty was in the correction of the core measurements, and then they defined an uncertainty range based on the core correction factor. So I followed that same path, and following that path, basically, my correction factor range was from 1.1 to 1.25 realistically for for the conditions that were actually present. And so I felt like the 1.22 that I originally used was a pretty reasonable place to be. So I didn't make any changes. So to answer your question, yes, I used the experience and a rule of thumb, but I backed it up with a rigorous analysis that proved that that rule of thumb really wasn't a bad place to be. Our core guy, Jake Grethmel, is probably one of the best core analysis people on the planet. And he developed that rule of thumb so that young engineers could apply it very easily and not have to go through all the rigorous analysis that I ultimately did.
So has this been a normal practice in our industry, that we always apply a correction factor to, let's say, a core measurement?
Yes, yeah, that's standard practice.
And did you check, since you said it is a standard practice, did you check, assuming Core Lab did perform this core analysis, right? Did they apply the correction factor or not?
They do not. They don't report it. They report the saturations as measured.
Okay, let's move to slide number 4. So there has been a lot of great discussion about the rock types, and then even looking at your cross section right there, you've talked about the cast and then also the collapse. My question to you is, and this will be the first question, I do have a series of questions on that. How does that impact CO2 EOR, assuming, let's say, Empire is to embark CO2 injection into the San Andres?
Well, again, I look at the San Andres, the shallow part of the San Andres, above what I've defined as that gamma ray marker. I see that as a situation where the karst they're certainly present, and I think they potentially would be much more limited in aerial extent than they would in the upper San Andres, because they were created from exposure, surface exposure of the carbonate ramp at the ramp crest periodically, and meteoric water, rainwater basically, moving down through that and creating dissolution of the carbonate materials. And so that's more of a typical karst that you see in a ramp environment. And so again, this is my opinion, the CO2 operations would be probably could be potentially advantageous in that environment, but because the karsting wouldn't have large aerial extents. However, when I moved down into the San Andres interval, which I call the lower San Andres, but below that gamma ray marker, that interval appears to me, at least, to have been more affected by the massive water and CO2 movement that Dr. Lindsay and Dr. Trenham have hypothesized. And those karsts would be developed post-depositionally at the time that the Guadalupe Mountains, I don't remember what the proper geologic term for the uplift that occurred, but the rock had been uplifted and the San Andres was exposed at the surface, and you had meteoric waters moving through. There were, in Dr. Trenham's model, and it may be Dr. Lindsay's model, I don't know who actually came up with it first, but there was first a hot water, geothermal water moving through there as a result of volcanic activity near the mountain ranges, and then there was there was a further uplift that shut that hot water off, and then you had cooler water that was just migrating in from the outcrops. And in their model, I think they've hypothesized somewhere between 15 and 24 volumes of water have moved from that mountain range across southeast New Mexico and into the Central Basin Platform. Now, Dr. Lindsay has a theory that H2S was coming out of the oil, the Wolfcamp oil was being liberated, and it was moving the other way. Since the water would be moving downhill from the mountain range into the Central Basin Platform, and gas, because it's lighter density, would be migrating upward. So he has kind of a cross flow. And the commingling of that fresh water and the H2S would create sulfuric acid, and I think that's a perfect recipe for karst. In fact, I think that's the theory for the development of the Carlsbad caverns, if I'm thinking properly, the H2S and the meteoric water is what leached out the Carlsbad caverns. And, I'm convinced, based on you're looking at the gamma ray, seeing that there's smaller grain size material down in that lower San Andreas, the fact that they're able to inject on vacuum, and they're able to inject thousands of barrels a day and over long periods of time, not seeing much of a pressure increase, that seems to me to indicate that the aquifer is very large, and the permeability that allows that to happen would have to come from karsting environment. So so I think that the lower San Andreas may fit the Trentham-Melzer model extremely well. The upper San Andreas may or may not fit that model. It seems to be that the karsting is more localized, but again, I haven't looked at all the data, and that's just an opinion. I'm certainly not an expert on any of that, but I'm relying on the expert testimony I've heard to give you an opinion on the different styles.
Well, so from the cross section that we are seeing here, which I believe was slide number 16, so all the I believe all the purple or the violet color, more or less showing the cast.
Right.
Okay.
And what this is actually showing is the existence of what I think are bedded anhydrites through that yellow interval. And if you get below there, if you look at my computed well logs, you'll see that the porosities below that highlighted interval start getting very high. For example, in the outcrop and up in the chord interval, the average porosities of each of those rock types are in the vicinity of maybe 8 to 10%. So the porosities in what Trentham and Melzer would call the main production zone up there would be in the 8 to 10% range. The core data pretty much is consistent that you don't really have high porosities in that chord interval. However, if you get below that yellow highlighted interval, you get into long intervals where the porosities start to approach 20%. And the other thing that you see in those intervals, again, if you look at my computed logs, is the resistivity falls to very low values. And those two conditions together indicate that there's quite a large vug volume in there. And the fact that they lose circulation as soon as they drill out of the bottom of that yellow interval and they lose returns suggests that there's very high permeability down there that will allow a lot of fluid to flow, and they're able to inject 120,000 barrels a day or more into that interval, and they haven't seen any major pressure increase. To me, that suggests that the presence of a karsted system.
Well, so my question was very simple. Within that yellow shaded region, you're saying that there are a lot of cast in there.
There could be karst in that interval as well, but the anhydrites would be the anhydrites that would be indicated by those little flags would tend to isolate those intervals from one another because the anhydrite is going to be impermeable. It's impermeable. And if they're layered, bedded anhydrites, they would present barriers to vertical flow.
So those violet flags are not cast, but
No,
anhydrites.
those are the bedded anhydrites as I've interpreted them.
But I thought one of your slides, you were showing that those are cast. You use that same color.
Oh, well, I apologize for that. Again, I'm colorblind and maybe I choose things wrongly, but those flags in that exhibit are bedded anhydrites. Your question, could there be karst between those bedded anhydrites? The answer is yes, there could be. But the major karsted intervals are those below that highlighted yellow interval down in what I call the lower San Andreas or the injection zone.
So what will you term the yellow shaded region?
In my view, that's a region that contains multiple potential vertical permeability barriers in the form of bedded anhydrites.
So you're saying that the entire yellow shaded region is anhydrite?
It's not anhydrite. The anhydrites that bedded anhydrites are denoted by the little flags. And you see that they exist in all the wells. Now, you can argue that, well, they don't exist. You can't correlate them. And I would agree with that. You can't correlate one bedded anhydrite all the way across the field. However, there are enough of them that I think in mass that they provide a reasonable barrier. Now, Mr. The Counsel for Empire, I'm sorry, I'm getting really tired, but Counsel for Empire wanted me to say that I'm 100% sure that those are barriers, and I'm not. I don't know that I can map them all the way across. However, the preponderance of the data, when you look at slow circulation, you look at the injection volumes, you look at the fact that we don't see direct evidence that major water is moving up, that's impacting the Grayburg water flood. In other words, we're not seeing that we're producing way more water than we're injecting, which would imply that there's major communication up. My conclusion is the preponderance of the evidence suggests that yellow interval is providing reasonable protection between the injection zone and the water flood operations above that yellow highlighted area. And until we see evidence, concrete evidence, by way of pressure or the fact that we're producing more water than we're injecting, I'm pretty comfortable in saying that I think those two zones are isolated from one another.
Okay. So you said that there might be some karst present within that yellow shaded region. At the same time, you do have anhydrite. So those are two things.
Right.
Now, is there a situation where, based on the karst, there could be a potential conduit between the Greenback and then the San Andreas?
There certainly could be a potential conduit, but again, I haven't seen evidence of it.
Okay. So if you look at Dr. Backwater's model, Mr. William West really made it clear to us about the production history. So there was a map, there was a bubble map that showed the oil production and then also water production. So when you say that we do not, so the karst could be a conduit. Now we are all petroleum engineers. So I want you to comment on the scenario where he also said this could be fractures that are existing, local fractures that are existing. And then he utilized that in his simulation history matching effort. So can you tell the commission that strategy that he used, looking at existence of fractures in the core, and then even you've also added karst to it, is there any strong evidence to suggest that what he did was wrong?
Well, I used to do a good amount of reservoir modeling early in my career. And to be honest with you, the reason I moved more into petrophysics and reservoir description is because I found that I could make a reservoir simulator do dang near anything I wanted. I think your experience is probably the same. So what it told me was that we needed to spend more time doing the reservoir description before we started simulating. And I guess the things that bothered me a little bit about Dr. Buckwalter's model was that, for one, he modeled the entire San Andreas interval. I guess, from he moved the water contact down and then modeled everything under the water contact with like a 6% porosity and a single permeability. Well, you can see, again, it's not clear on this particular cross section, but if you go back and look at the computed logs, and it doesn't matter whether you're looking at my computed logs, Newtek's computed logs, or Ops computed logs, when you get down into the lower part of the San Andreas, the porosities are not 6%. They're, they get up, I don't know what the average would be, but you get porosities in the, up approaching 20% down there. So the fact that he used a 6% porosity, in my opinion, too low of a permeability to represent the aquifer. If you choke the aquifer with low permeability and you restrict its volume by using too small of a porosity, well, of course you have to have a large volume to explain the pressure response you're seeing. And I would argue that he might have been able to do exactly the same thing if he modeled what I call the upper San Andreas above that yellow area and modeled it with a high permeability and with edge water drive coming in. He might have been able, and again, his was not really a simulation. I saw it as more of a large scale material balance model. And I think you could probably build a material balance model that would explain the same thing with not having to include the San Andreas from the oil water contact all the way to the Glorieta and come up with an identical history match. Now, I haven't. Now, you're going to say, well, have you done that, Dr. Davidson? I'm going to tell you, no, I haven't. But I'm just saying those are the things with the Buckwalter model that made me nervous that I would have done differently had I built the description for it.
Oh, Dr. Davidson, so my question was very simple, In our reservoir engineering principle, when we have a higher water production well localized, similar to what was shown to us by Mr. West with that bubble map, I'm asking you a very simple question. Is it typical in the oil and gas industry that with the knowledge of fractures from a core, and then also with the cost that you've even added to it, it is reasonable for a reservoir engineer to assume that there could be a localized either cast or fracture causing this high water production?
And I would agree with that. It's a reasonable assumption. Where I differ from Dr. Buckwalter is that I think that water could be edge water coming in through karsted system through a tortuous pathway from the edge. It could be water coming, from the upper San Andreas at a localized area through a karst. The other thing that nobody talks about that I have experience with, a lot of the early wells were open hole completions completed with nitroglycerin. And it's perfectly possible that water could be entering from the San Andreas into those well bores and then migrating to the place where they saw the plumes. I don't know that that's the case. I just know there's multiple possible scenarios that can explain those high water. They don't all necessarily have to go back to point out that the lower San Andreas is communicating all the way up through fractures or karst or whatever.
Dr. Davidson, so I think you and I agree that that is an option, and as a petroleum engineer, you have multiple options that is on the table. But when you chose that strategy, you and I agree that it's not wrong. Now, my question to you is, you're describing to the commission all the other potential options that could have happened. Why did Goodnight not perform similar reservoir simulation model to debunk Dr. Backwater's scenario?
I don't have an answer to that question.
Okay, let's go to slide number 6. If we can go to slide number 6. Okay, okay. So there's been a lot of discussion on this slide as well. I want to ask you, can this approach, using, let's say, resistivity index and all of that, can that equate to the Archie's equation?
Yeah, you could get to an Archie's equation from that. The problem that you wind up with is if I used Archie, every point on that cross plot would have to have a different N value in order to return the proper saturation. And the beauty of and I can't remember the gentleman from Schlumberger who designed this, but the beauty of this model is with those SC curve fit values, I could represent a whole range of RI values with a curve fit model. It's simply easier. It's easier to calculate. Now, what I could have done, which would have been very tedious, is to go through and use the SC value to calculate an N value, and then use Archie, the normal Archie's equation with the N value derived from the SC curve fit. And I could have used Archie's model, or I could use the equation at the bottom left-hand corner of that slide, which uses the SC value directly with the resistivity index. So we chose to go that route because it makes the computations much easier.
It makes the computation so much easier. So your testimony is that the San Andreas is oil wet reservoir. Is that correct?
I think that's correct. And the reason is not because of any particular attributes of the San Andreas in and of itself. It's because of the relative ratio of asphaltenes to lighter hydrocarbon components in the crude. Most people believe, and fingerprinting has shown, that the majority of this crude probably originated in the Wolfcamp. In the Wolfcamp, the asphaltene concentration is relatively high. And when you get a situation where you have high asphaltene content, rocks, regardless whether they be clastic or carbonates, tend to become oil wet. And it has to do with van der Waals forces at the surfaces and the fact that the asphaltenes are polar molecules.
So is it your testimony that the oil that probably might be in the Greenberg and then the San Andreas is from the Wolfcamp?
That's what the general consensus in the industry is.
Okay. So when Empire Expert says that the reservoir might be mixed wet, what is your comment on that?
It could be mixed wet in a situation. Let's kind of derive the series of events. When oil is migrating, it migrates as though the rock is water wet. In other words, there's water on the outside. The oil migrates through, to the point where it gets into a trap. After it's trapped, there's in millions of years past, there's plenty of time for those asphaltenes to be attracted to the surfaces of the carbonate grains, and it flips wettability from oil wet to water wet. And in most carbonates tend to be oil wet. Now, a mixed wet condition can exist in a situation where you have very high mud content, mud particle content. And in that world, because the pore throats are so small and the van der Waals forces that are attracting the polar water molecules, those forces are so strong that the oil can never penetrate in there to begin with. In that condition, the larger pores in the system would be oil wet, and what basically would be the mudstone or the mud component of that could still contain water. And that creates a very complicated conductivity environment. And that's part of the reason that, particularly when we get down to the mud-dominated pack stones and the wax stones, that behavior becomes highly nonlinear because you have a very complicated conductivity system, where some of the currents passing through the mudstone and some of the currents trying to pass through the larger pores in the other portions of the rock.
So, Dr. Davidson, are you saying that, let's say you've based on your analysis, you're saying that it is oil wet reservoir?
I believe it's predominantly an oil wet reservoir. Okay, I'm sorry.
Yeah, so I'm just asking a very simple question. And then Empire experts are also saying that it could be a mixed wet. Now, based on your based on the discussion, it sounds like you believe that this reservoir could also be a mixed wet.
There's portions of it that could. The portions that contain very high volumes of mud-sized particle, you could have a mixed wet system. But
okay, so if you have a mixed wet system, now what are the assumptions that you utilize on this particular slide?
well, again, I'm taking the saturations as they appeared in the core, and I'm plotting them versus the resistivity index, and I'm fitting a model by rock type to each one of those clusters of data. So it really wouldn't, the wettability, while I believe it's an oil wet reservoir, and arguably one of the methods that, for example, one of the methods that's used to identify the presence of an oil wet reservoir is to create a plot just like this. And this comes from Jerry Lucian, it comes from George Asquith, and it comes from the folks from Schlumberger. When you make this cross plot, if the majority of the data fall above the n=2 line, then you conclude that the reservoir is oil wet. That's one of the uses of this cross plot in the industry. But regardless of the wettability, I've taken the core data, corrected it, plotted it on the cross plot, and I've fit a model to the data, the corrected core data. So the model is going to be applicable whether or not it's fully oil wet or partially water wet or mixed wet or whatever, because I've built a model that's calibrated to the actual core measurements.
So is it your testimony to the commission that it doesn't necessarily matter the type of wettability? Your analysis is still valid.
That's correct.
Now, the M&N more or less inherently, some way, somehow, can be within this equation.
Yeah, you could turn this into Archie if you wanted to.
And is it your testimony that the wettability doesn't impact the rock type?
No.
Not at all?
No.
Okay. So on this particular map, on this particular plot that you're showing us, can you identify oil saturation is above 20%?
Well, yeah, they would be a little bit difficult, but they would, whoops, we just lost it.
Yeah, we can just draw a line.
But yeah, you just draw,
Yeah, just draw a line.
The it's a log scale, so it's not trivial.
Okay. Mhm.
It's 0.1 on the left and so it'd be probably a little, see the 0.69 down there at that green arrow. It would be the 80% would be somewhere to the right of that, between that 0.69 and 1. And so log scales, yeah, maybe about where you got the cursor.
So when we look at that, and then you're saying that these points are all saturation points from the EMSU 679.
They were above 80% water saturation, or they wouldn't be plotted on there, the points above that line.
Now, I'm just asking you that these points that you are showing us, whether it's a complete points or not, these are all actual core measurements from the EMSU 679 well. Is that correct?
That's correct.
And we've established that there are oil saturations above 20%, as you've plotted here. Is that correct?
Yes.
Then tell the commission why you say that there is no ROZ.
I didn't say there's no ROZ in the upper San Andreas. Again, I may have a little bit of difference of opinion from Trentham and Melzer. When I look at actual ROZs that have been established, I see a pretty repeatable profile and saturations from the top of the ROZ to the bottom. And I don't see that nice straight line at about 40% in the 679 or the RRBL data. That doesn't mean that it's not an ROZ. It just means it doesn't have a profile that matches what other ROZs have. And I would be perfectly happy if Empire went in and installed a CO2 project in that upper San Andreas and made money with it. It would be great. My contention is that the injection operations that are occurring below this little yellow band are not likely to impact it.
Well, so, let me pick up on your last point that you made, your last statement. You said that it will be great if Empire can go in there and do CO2 project up in the upper San Andreas.
Yeah.
Is that not what they are requesting from the commission?
Yeah, but the problem that, as I see it, is they're trying to shut down injection operations in an interval that, in my opinion, is not affecting their potential ROZ development in the upper San Andreas. I think both companies can continue on and not interfere with one another. And at minimum, we could probably install some sort of a monitoring process to ensure that they're not interfering with one another and come up with a way to handle it if there is, if communication is established. But I don't see anything right now that's preventing Empire from moving forward with the development of the ROZ in that upper interval. And I don't think that the injection operations below this little yellow band are necessarily endangering that project.
Well, Dr. Davidson, so is it your testimony? Are you concurring with Empire that at least there is an ROZ in the San Andreas?
I think there's indications there's one in the upper San Andreas above that, what I call the gamma ray marker.
So is it your testimony that, because Mr. Macbeth was saying he used a statement called, I forgot, he used alleged, thank you. He used alleged
resources.
ROZ. Now, he said alleged ROZ.
And to my understanding, Mr. Macbeth's testimony was concerning the interval beneath this yellow, in the San Andreas beneath this yellow band.
I don't remember.
In fact, if the testimony was, he went in and took the San Andreas interval above that yellow band, calculated the oil saturations in there, and came to the conclusion that the economics may be questionable. But then when questioned on whether or not there was an ROZ that existed all the way down to the Grayburg, I think he coined the term alleged resources for that. And we're talking about two different San Andreses, in my opinion.
Well, so is it, I mean, we're all here. I don't think Mr. Macbeth showed us even the anhydrides, the cast, the yellow shaded regions that you are referring to. I mean, there's a first time I'm seeing that. So he said there is an alleged ROZ, but based on the discussion that we're having now, it sounds like you're saying that at least there's just ROZ in the Upper San Andreas.
I think there very well could be. But again, I have a different opinion. I think they look more like migration pathways. They may or not be aerially continuous, but I can't say with certainty they're not there. They've seen residual oil in the two wells they've cored into that Upper San Andreas. And again, if Empire feels strongly about going for it, that I think they should go for it. But I don't think the injection operations deep are going to impact it. And I think the commission could probably put in place some monitoring protocols to make sure that they're not interfering and come up with a game plan to how to move forward if interference is ever found.
So, Dr. Davidson, on your cross session that has been that we've seen there, using the yellow shaded region as your reference, where is the Upper San Andreas?
Well, again, I don't know where the top of the San Andreas pick is. And I don't know, to be honest with you, I don't know what anybody does, but it would probably be this little region right in here. Yeah.
For record reference, indicating about 4 inches above the yellow deal.
Yeah. So and again, I don't have the tops. I don't think I have the tops on here. But this interval here is probably the Grayburg. This little interval right down here would be what everybody, in my view, is calling the Upper San Andreas. And the ROZ, I think, resides along this interval. And then we have a long interval that is this high frequency interval where I think we potentially have the bedded anhydrides. And then the injection operations are occurring down here. And then that's the 700 TBB down below this interval. And the fact that we can drill through this thing, move circulation down here, we can inject down here for long periods of time and don't see pressure increases, which indicates it's a very large aquifer. And thus far up here, I haven't seen concrete evidence that that significant volumes of water are moving up such that the produced water volumes exceed the injected water volumes. So, and again, I'm in the position, and I'm just saying the preponderance of the evidence at this point that I can see indicates that they're two different systems.
So, Dr. Davidson, the yellow region.
Yes, sir.
Now, the anhydrides that you've picked,
Mm-hmm.
do we have any core data supporting that, or mud log data supporting that?
Anhydrides show up in the mud logs, but they're not going to be able to tell whether they're bedded or not. That conclusion becomes from my viewing of cores, particularly the level and slaughter area where you see this, the combination of elevated gamma ray, the low porosity and the high grained and high bulk densities indicating the presence of anhydrite. And Jerry Luce had developed a cross-plotting technique to identify bedded anhydrites. In those intervals, they fit the fact that there's elevated gamma ray. They fit the fact that the density neutron cross plots indicated the presence of anhydrite. The mineralogy model suggests the presence of anhydrite. And I've seen this log signature in places where core data exists, embedded anhydrites have been observed. Have I seen core in the EMSU in the San Andreas that shows bedded anhydrites? I have not. This is just based on my experience.
So you've not, and even based on the cross examination, it sounds like you cannot put on record that you believe that this is a barrier to, let's say, flow.
I believe it's a barrier to flow. I can't say with 100% certainty that every one of those is embedded in hydride.
So then, and you also testified that the commission doesn't need any additional data.
I don't believe so. I think that there's enough data from the injection, the lack of interference, the lost circulation, that there's not communication between the two. Again, I'm just looking at the preponderance of the data that I see, and I would argue it may be very difficult to get reasonable core data down there because of the lost circulation issues.
So let's go to slide number 5. Right here. So this is the rock type analysis that you perform. Is that correct?
Well, this is based on the outcrop analysis, and these were averages of the petrophysical properties for the different rock types present. And what I was trying to show here was there's not a very big porosity variation, but there's a big permeability variation, and it's therefore important to try to identify the different rock types in the petrophysical parameters when you're doing an analysis of this type of ramp environment.
So did you utilize this rock type that you've developed based on an outcrop data for the subsurface analysis?
Well, the process was this: the Bureau of Economic Geology was tasked with developing a model that could be applied in a carbonate ramp environment, and they identified the major rock types that are available or present in a carbonate ramp environment. And then what they did, they went to the outcrop. They dug down into the face of the rock outcrop to get the surface weathering features off. They collected core samples they identified the rock types present, obtained core samples out of the rock type. Then they took those core samples and they cross-plotted them by facies type, for example, grainstones. They cross-plotted all the grainstones together on the porosity permeability cross-plot, and they defined a region on that porosity permeability cross-plot that is associated with the grainstones. Then they did the same thing for example, for the mud-dominated pack stones. They collected several samples of mud-dominated pack stones. They plotted them on the cross-plot. They found that they existed below the grainstones in a translated, density neutron cross-plot trend. They did the same thing for each one of them. And then they went through and they said, okay, for each one of these, and Jerry Lucia calls them classes rather than rock types, but for each one of these classes, I'm going to determine an average value, a standard deviation, and I'm going to create this cross-plot model so that anybody could take core data, put it on this cross-plot where we've identified the region associated, the porosity permeability region associated with each of these different rock types, and they could make a preliminary estimate of what the rock type is. So I did the same thing with the MSU 679 data. It was I found and I took Jerry Lucia's cross plot and I plotted all the core data up. I selected for example, there's a band of data that represents the grainstones that they found in the outcrop. I took all of those grainstones, the core samples that fell within that grainstone cross-plot region. Then I plotted them on that RI versus SW plot, and I did a curve fit of that SC value through those grainstone values using the log saturations. That provides a reasonable estimate of how a grainstone would behave as a function of RI given the corrected oil saturations and water saturations that were measured in the core. And I used that model rather than an Archie's model because it's much easier to use than trying to come up with a variable N model. And I tried to demonstrate that the variable N model is somewhat difficult because for a particular porosity, there's a variety of N values that can occur. So then you have to go in, you have to do the same thing. I could have done the same thing with Archie, granted, if I wanted to go to the trouble to come up with an N model for each rock type. But this SC model is so much easier and faster to calibrate. I used this Schlumberger model because it's simply much easier to use than the Archie in this environment.
So it was a simple question. Well, let's go to slide number 11, and I'll try to wrap up here. So here I'm asking you, do you see any oil saturation within the San Andres?
In the San Andres, as it's defined here, it's below that region of the high frequency. If you see, and I can't see the depth, move your cursor up to that gamma ray, maximum gamma ray. It looks like it's about 525. So that interval from 525 go down about an inch on this thing. That's that high frequency interval. And what I think this is one of Preston's picks. He's picked the San Andres to correspond to the interval that's the injection zone. And that, again, I'm not going to get into the pick argument. It's just that just happens to be where this San Andres is. If you go down, you'll see in the oil saturation track, periodically I do calculate relatively high saturations. I mean, there's some up to 30 and 40% in there. They show up periodically up and down the system. So yes, there is oil down in there. They tend to be associated with some of the lower gamma ray readings, and that makes sense because the lower gamma ray readings down there in that yellow San Andres interval correspond to the grainstones and the better rock types. So yes, there are grainstones and better quality rock types all the way through the San Andres. It's just as you get deeper in the system, you see the gamma rays starting to get higher and higher. That's indicating a higher mud content. But when the gamma ray does clean up and the resistivity is high enough, we do get oil saturations down in the San Andres. The problem with that, I mean, so yes, there's oil in the deeper San Andres. The problem is they're separated by hundreds of feet. They don't necessarily have the profile. If you look on the right of that diagram for the Seminole San Andres unit at the water saturations in the right track there, you see that there's kind of a wall of 40%, 45% saturations from the top of the interval to the bottom of the interval. When I'm looking at the oil saturations, for example, at the bottom left of the EMSU 746, they don't really have that flat profile. In my view, those are more indications of abandoned migration paths. I may be wrong on that, but in my view, that's what they are. They certainly don't seem to represent the profile that I would associate with an ROZ. The other problem is that the majority, when I do calculate the presence of oil, the majority of it is less than 20%. And Dr. Trentham excludes intervals with less than 20%. Opsin excluded intervals with oil saturations less than 20%. We exclude oil saturations less than 20%. If we go over here to the right, and let's go up to what's the MPZ in the SSAU. Can you put the cursor up there for me? That interval, if that's been CO2 flooded for over 40 years, and the oil saturations don't rarely exceed 20%. So to me, that tells me CO2 is not going to be effective at oil saturations at 20% or less. And Dr. Trentham agrees with me on that. And so in my view, counting the oil saturations less than 20% down there and including that as potential economic oil is not prudent. There are some intervals, and if you look down there, particularly at the bottom, let's go down to the bottom on the 746. There's some intervals up there that are 30 and 40% oil saturation, but they're very thin. And in my view, they're probably not ROZs. They're probably migration paths, but there's just not going to be enough down there, at least in my opinion, to be economically attractable to go after. And if they're migration paths, they're not going to have any aerial continuity. And if there's major karsting down there, it's going to steal the CO2 and prevent it from being able to displace any of that in the first place.
So, sir, as a petroleum engineer, and based on your extensive experience, I want to ask you, what is the typical residual oil saturation to CO2 injection?
In my view, it'd be about 20%.
Residual oil saturation to CO2 injection.
CO2, yes. Now in the lab, they can get it down to about 12%. But the problem is in the lab, you have a confined tube and the CO2 can escape. In reality, when you have unconfined CO2 injection, dispersion will drive a bunch of that CO2, unless it's confined between very, very good barriers, dispersion will drive it out, and you don't get a nice sweep across the entire interval. And I go back, the interval in the MPZ on the right has been CO2 flooded for 40 years, and there's very few saturations less than 20%. So I think that's kind of the bottom in a practical field operation. That may be the bottom, and it's not because the CO2 couldn't do it more. In a core plug, you can get it down to maybe 12 to 14%, but in a reservoir, dispersion kicks you out where you can't really get it that low.
Does that help me understand why in our industry, where let's say oil saturation, irreducible oil saturation to about, let's say residual oil saturation to about 27%, 25% is where we kickstart CO2 injection.
And yeah, and I believe that. And what you find is that you get a lot of the oil between 20 and the 27%. And if you've got a lot of area, that can turn out to be quite a bit of oil.
Well, I'm not sure any company that will go in and say that I do have movable 7% saturation points that I'm going to throw in huge amount of capital to proceed with the CO2 injection.
I wouldn't put a large amount of money into doing anything when the saturations are less than 20%, because I don't believe it's been demonstrated that you could reduce the saturations much lower than 20%. And I think Dr. Tranham would agree with me on that. But I actually did the analysis. I mean, it's in my write-up. I went back and looked at Seminole. Seminole is very well defined in their CO2 project. And I went back and I did the analysis. I said, what was primary? What was secondary? I calculated in the main production zone what the average residual saturation post-secondary recovery was. And then I looked at what happened, what the projections were going to be post-CO2. And basically, I found that if I took the residuals that were present at the end of the water flood and reduce those residuals down to the 20%, I was able to match the production, the CO2 performance that they actually obtained. And that was a method, a secondary method, and it's in my rebuttal testimony because I got such pushback on why this 20%, why are you excluding intervals that have 20% oil saturation? They're going to sweep too. And I'm like, well, there doesn't appear to be any indication of that. So I went back and looked at Seminole, and when I did the analysis, I showed that, yeah, you could, the average post-water flood, the average residual was about 35%. If I take that 35% and reduce it to 20%, I can reproduce the recovery that occurred from CO2.
So, sir, when we say that typical, based on Steve and then Bob testimony, they define ROZ more or less from 20% upwards.
Yes, sir.
So are you saying that that is a wrong definition?
No, I think that's a perfect definition. They're smart enough not to include intervals with oil saturations below 20% in their in-place estimates when they calculate the ROZ potential. Now, I'm not saying that don't count from 20 down. If an interval's got 35% oil saturation, you count the entire oil saturation. I'm just saying that if an interval doesn't have it doesn't exceed 20%, it's probably not going to flood economically, and it shouldn't be calculated in the in-place. The recovery factors are based on the in-place estimates, right? And if you look at Seminole and you look at the in-place estimates on the intervals above 20%, and you calculate what happened, what you find is that they got roughly 25% of the oil that was in place in the intervals that exceeded 20% oil saturation. That recovery factor goes with that oil in place. Now, if we'd included the whole interval, that all oil is oil, it's all oil in place, then that recovery factor would probably fallen down to 5 or 6%, which is fine. But you've got to understand that recovery factor and in place are implicitly tied together. You cannot separate them. And if you're going to include oil that's not going to move, then you've got to reduce the recovery factor to account for the fact that it doesn't move. And as a result, Dr. Trentham and Melzer have basically said 20% and above is what we need to calculate, that we need to consider as intervals that contain ROZ that's commercially retrievable.
So you also talked about using the 7% cutoff. I mean, you said that is an industry practice. Is there any reference to a carbonate where 7% is used as a cutoff? Any reference that you can share with the commission?
Well, you could probably go up and look at the Mount data. I think they use 6% there. The industry standard, to my understanding, is typically for carbonates on conventional analysis, conventional water flood, primary production. You usually use a 1 millidarcy cutoff. And then you look at your porosity perm, because we can't calculate permeability with well logs. Some people think they can, but in reality, we can calculate porosity, we can calculate saturations. If we have core data, we can build a porosity permeability cross plot, and then we can say, okay, let's look at down there. In most cases, you say, okay, for an oil, we'll use 1 millidarcy, and then I'll curve fit that line, and I'll say, okay, at this point, I've got as many points that I'm excluding that are above 1 millidarcy as I'm including that are below 1 millidarcy. So I'll use that porosity cutoff in lieu of a permeability cutoff. And I'll say that porosities below that interval, below that level, are non-reservoir. I didn't want to be that strict. So we actually went, because again, and you made the point, because this is gas injection and gas can move in places that liquids can't, I said, okay, let's use a 0.1 millidarcy cutoff. And that 0.1 millidarcy cutoff with the 679 data indicated permeability, a 0.1 millidarcy permeability cutoff corresponded to about a 7%. And I went and talked to Bill Knights, who's our geologist, and I said, what are people using for cutoffs in the San Andreas? He said, well, generally somewhere between 6 and 8%. And I said, fine, we're right where everybody is. So I was comfortable with that. And I was comfortable with it because we allowed the fact that not using the traditional 1 millidarcy going to 1/10 of a millidarcy, because we were evaluating a potential CO2 operation rather than a water flood operation. So it was a little bit more inclusive. I felt like I was being generous. And the Empire and those folks are going to say, my God, you're killing us. It's a 4%, and there's different opinions on that. And believe me, as a petrophysicist for a reserve consulting company, cutoffs come up every day and I get hammered. I've never been right in my 45 years on a cutoff with anybody else. They're always arguing it needs to be different than what I've selected. So, I've got a pretty thick skin on that. I get criticized regularly for my cutoffs.
So my question to you was, do you have a reference, documented reference
Well, I can
to show the commission?
I guess I could show you where, for example, at Maljamar, in their water flood study where they did the pressure core, their oil in place estimates are based on a 6% cutoff, but on the other hand, that's better quality rock in the upper St. Andrews using a 1 millidarcy cutoff. So, I would say that I'm even more aggressive because I'm using 1/10 of a millidarcy in the porosity that goes with that. I can show you that reference. I've got it with me. We can take it out and look at it if you want to see it. But as far as are there general references that say what the cutoff should be, I haven't seen it. And if there are, I haven't found one that I can show you.
Yeah, so I was curious. During the cross, you said in the industry we use 7%. So I was curious to know that. Now, my last question to you, hopefully to be the last question, it depends on how you respond to it. So, are you familiar with the water withdrawal wells within the vicinity of the EMSU? Now, so you do have excessive high volumes of higher salinity water injected by Goodnight into the San Andreas.
Right.
Don't you believe that at some point that injection is going to impact the water supply wells where you have higher salinity with different type of TDS, different types of, let's say, composition withdrawn and utilized as a water flood in the Greenberg? Is that not going to impact the activity in the Greenberg?
Well, yeah, and again, I haven't looked at where the water supply wells are completed. I mean, I would have to think that if the water supply wells are all the way down into the lower, and you continually inject high salinity into the lower San Andreas, that you potentially there's going to be communication. However, the other option is to take water out of that interval, that shallower interval above what I call the gamma ray marker. But again, those are operational considerations that will have to be considered. As I guess at the end of the day, I think both of these companies could get along just fine, and a equitable solution to this problem can be found. And it may mean that different water supply wells have to be drilled other places, and it may mean that we have to install pressure monitoring and all those sorts of things. But I don't see any reason why both of these projects can't go on. And that's just my personal opinion. Nobody from Goodnight talks to me about this stuff. It's just me looking at the practical aspects and wanting the best for everybody. I want everybody to succeed. Our company wants everybody to succeed. What we try to do is identify risk and help people make the best decisions possible. And when I look at this, I think, guys, there's potentially some great projects here for everybody. And the disposal is valuable to the producers in New Mexico as well. They've got to have somewhere to put the water they're producing, or they're going to have to shut wells in. Those sorts of, there's a lot of people, a lot of moving parts of this thing. And in my view, it's one of those deals everybody could get along, and we just need to figure out how to work together on this.
Well, you said everybody can get along. So you are not aware of any discussion between Goodnight and Empire where Goodnight is proposing to Empire that just focus on the upper San Andreas and let's do our own thing in the lower San Andreas.
I wasn't involved in any of that, so yeah, I'm not aware of that.
So based on what you discussed, then could there be a scenario where the commission will say that, okay, let's give Empire the time frame they are requesting for probably 2 to 3 years, and let them do their characterization analysis and come back to the commission and prove to the commission that we drilled, we saw it, and it's recoverable.
That's fine, but I'm not sure that curtailing injection for the Goodnight wells during that process is necessary. Again, I think Goodnight could go if they wanted. I mean, Empire, if they wanted to go ahead and try to do the work to establish an ROZ in the lower, in my view, there's nothing right now from stopping them. If it's truly immobile oil, other words, it's not mobile, the injection operations aren't going to move it, and you could drill and core it and see whether or not an ROZ profile exists. I don't think there's anything from stopping them from doing that. For whatever reason, they're hesitant to make that jump. And again, when you look at the big picture of everybody that's depending on this disposal, and the fact that it's an ROZ and the oil's not mobile, and this is just me, I don't know why you couldn't go out and drill a well if you wanted to do it and core it right now, because the injection's not moving the oil anywhere. What you're interested in is there an ROZ in that lower section? And I don't see any reason why they couldn't do that, and I don't see any reason why injection couldn't continue why they do it, and I don't know why they're not doing it. You'd have to ask them that, but I'm looking at it and it's like, I don't see any real reason to change anything until there's definitive evidence that you need to.
Thank you, sir, for your testimony.
Thank you, Dr. Ampoma. Mr. Lampkin, questions for Dr. Davidson?
Yeah, I have a couple. Good afternoon, Dr. Davidson. Thank you for your testimony. With regards to this slide that's up right now, did you perform any analysis on other wells that were logged through the lower San Andres to see if their saturations conform to what you found in this well?
Well, we did what I was able to do. The wells that penetrated into the San Andres that were available to me, some of them didn't penetrate all the way through. I was also able to, the other thing that we did is I had wells inside the EMSU that were disposal wells and a few wells outside the boundary of the EMSU that were disposal wells that did penetrate the entire section. And yes, we did find evidence of small intervals of residual oil up and down the system, much like is displayed in this exhibit here, one that you're looking at. However, when we made efforts to try to correlate them, can we correlate, aerially, we couldn't really correlate them very well. And when I saw that, I'm like, well, there's not a layer that exists over long, or we couldn't identify at least a layer that exists over long intervals or a big aerial extent where they're correlatable. That's part of the reason I came to the conclusion that I think they're migration paths. But there's probably a whole lot more wells out there that could be interpreted that we didn't have access to. But I'll tell you, of the wells we had access to, all of them had little tiny intervals here and there of oil saturations in them. And I wouldn't expect it to be anything different. I mean, hell, this thing, oil migrated through Southeast Mexico into the Central Basin Platform. The oil that's there, a lot of it came from New Mexico and migrated up into the Central Basin Platform. It'd be impossible for there not to be a little bit of oil through the San Andres. The question is, did traps occur in the lower San Andres that would create an ROZ? We can't see evidence of that. What we do see evidence of little elevated saturations periodically through the lower San Andres that thus far I've been unable to correlate from well to well, which indicates to me again that they're migration paths, not ROZs.
Okay. What can you tell the commission to alleviate any concerns that this was not a well that was cherry picked for low oil saturations in comparison to the other ones that you analyzed?
What you might do, I don't remember how many of the water disposal, I think there's the data set I had early on consisted of the 746 went all the way through. There's other wells that penetrate some distance into the San Andres. They're included in my original testimony. And then I think in the rebuttal, I included one of the outlier water disposal wells. I can't remember which one. It may have been Yaz, the well that is designated as Yaz. And you can see in those wells that, yeah, there's periodic saturations that show up. I'm not sure how many of the wells that in fact, I think we turned over all of them, didn't we? We turned over all the wells that I interpreted that penetrated the whole distance. So those PDFs are available. You're welcome to look at them and see where we actually did in each well, calculate a little bit of oil periodically. And I think there's 4 or 5 wells that we actually handed over that were water disposal wells, but they penetrate the entire interval. And you can see there's periodic oil saturations calculated in them. So we've provided that data.
Is that part of the exhibit packets that were submitted with the case?
I believe it is. Mr. Rankin, is that the case? I mean, it's certainly something we could.
My PDF is not cooperating, but I believe, Dr. Davison, that you included them as in your appendix to your direct testimony.
Some of them were in there, and we provided, after Ms. Shaheen determined that we used those, they were important, we provided them to Empire at that time. And so I don't know what the final disposition was. I know they've been provided to some of the parties here at least.
Good. Thank you for that. With regards to the lost circulation zone above the high gamma ray marker, have you seen any other drilling reports or mud logs or anything like that outside of Goodnight's claims that would indicate that is consistent across the formation in that area?
Well, again, this is my understanding. And so just understand this is what I understand from what I've been told. When in the wells I evaluated, I had Goodnight provide the top of the lost circulation interval for every well. When they lost circulation, I said, tell me where that top is. And those are posted. They're posted on my logs where the lost circulation occurred. Now, anecdotally, I've heard that the pilot and the other injection operators experience the same type of lost circulation when they penetrate these anhydride. As soon as they get out of the bottom of these anhydride intervals, that they lose circulation. And again, the pilot and the others could provide that information potentially. I haven't interpreted their logs. I'm told that lost circulation below this little yellow band is common with all the water disposal wells that are present. I can't confirm that. I do have lost circulation tops for all the Empire wells. I mean, all the Goodnight wells, and it's consistent that once you get down into this interval, loss. And I'm told, that tens of thousands of barrels are lost, and they drill for long periods of time with no returns. And that's when I found that out. That's when I said this thing's got to be karsted. You just don't get that kind of behavior. And it's always been unusual to me that we could drill entirely through the Grayburg upper San Andres interval and maintain circulation. It's roughly the same pressure. I think it's 1,300 PSI up in or higher up in the Grayburg San Andres interval. It's maybe 1,500 PSI down below, right? But we can drill through that entire interval. And as soon as we get through into this interval with what I'm calling bedded anhydrites, when we drill out of the bottom of that, we consistently lose circulation. I'm like, how could that happen if it's not a karsted interval? And how could we have all this volume injected and not see a major pressure increase? And so I did the conclusion I draw from that is the aquifer is huge. And we have isolation, and Mr. Wayne, when I was trying to, pin me into a corner. Well, can you say for certain? No, I can't say for certain based on this diagram, but the preponderance of the evidence, at least I've seen so far, makes me comfortable with saying that this interval and this interval are separated from one another. And I think Mr. Knights is even going to talk about other potential barriers that exist in the upper San Andreas and the Grayburg that also help isolate these two. So it's not just me talking. There's going to be other evidence presented as well.
Okay. I think that leads into my last question, which was in the scope of work that you had, you didn't do any analysis into a barrier to fluid migration between the San Andreas and the Grayburg, just the lower and upper in San Andreas?
Right.
Okay. Thank you.
Thank you, Mr. Lampkin. Mr. Rosato's last but certainly not least, questions for Dr. Davidson.
Mr. Hearing Officer, I'm sorry, I'm having technical difficulties. I was trying to unmute. No, I do not have any questions. Thank you.
Let me ask you, Mr. Rankin, it seems based on everything we've heard from Dr. Davidson, which seems like everything he conceivably knows on this subject, do you have any redirect examination you even need to do?
Mr. Hearing Officer, I do, I think I would like to do a little bit of redirect with Dr. Davidson. Although it's possible that after I have an evening to evaluate it, I may curtail it significantly. There are a few points that Mr. Lampkin raised that I think I would like to address, and there are a few others that I would like to address as well. Given that we have, just about 20 minutes left before 5 o'clock, and it was a long day, I may suggest with the Commission's approval that we reconvene in the morning to complete the redirect.
Chairman Rosatos, what's your preference on that?
I'm good with that. We can call it a day. It's already 4:40. So why don't we call it a day and then we can start back up again in the morning.
All right. I mean, I assume this is a captive witness, that it's not going to inconvenience Dr. Davidson if we don't get him off the stand today.
I agree, and the doctor is tired. Thank you, doctor, for your time.
I think your voice needs a break anyway, Dr. Davidson.
That's fine. I'm happy to keep going on forever. And I can talk as long as you want.
All right. So let's break for the day and pick back up again bright and early and fresh tomorrow at 9 o'clock.
Thank you.
Thank you all, and thank you, Madam
We'll meet
Court
everybody
Reporter.
at 9 tomorrow.
Sorry.